Okay, so we're just going to recall some topics from the algebra course in preparation for the first midterm. First of all, we have the order of an element is the smallest natural number such that the element raised to that power is equal to the identity element of the group. Now we have a cyclic group is a group that contains a generator. A generator of a group is basically an element of the group such that the entire group can be written as the set a to the power n, where n is a natural number and a is the generator. So essentially, any element of the group G is an integer power of the generator of the group. Now, a group which has at least one generator is called cyclic. So we have some examples. First, the integers under addition is infinite cyclic. Its identity element is 0. Its generators are 1 and also -1. Okay, so in most scenarios, this is just a notation thing. The number 1 will be used for the identity element of the group. But of course, in an abelian group, such as the integers under addition, the identity element is denoted by a 0. And in this case, the generator is 1 of this infinite cyclic group, namely the integers under addition. Okay? Our second example is the integers modulo n, also under addition, is cyclic with generators given by the element 1. Of course, this is the equivalence class of 1 modulo n, or any element coprime to n. So any equivalence class whose representative within the set 0 through n-1 is coprime to n, okay? Namely their GCD, their greatest common divisor is 1. They share no common prime divisors. So any element coprime to n will be a generator of z modulo nz under addition. Now we have a theorem, the classification of cyclic groups. The group G is cyclic if and only if it is isomorphic either to z modulo nz for some n greater than or equal to 1, or to z itself. Of course, these groups are under addition. Now, this isomorphism is not unique if the generator of the group G is not unique. Okay? And the isomorphism is given by sending, essentially, the generator, or sending 1 in the integers, sending the element 1 of the integers to a generator of the cyclic group. This is what the isomorphism will be given by. Okay? Alright, so now we turn to the definition of a subgroup. Recall, this definition of a subgroup is also the definition of a group, because you can just take the two definitions. G is a group if and only if it's a subgroup of itself. Yeah, we're going to start by defining subgroups and then define a group as a special case of a subgroup. Okay, so anyways, so consider a group G with H being a subset of G. Then G is a subgroup if and only if it contains the identity element, it is closed under the multiplication operation given by G, and it contains inverses, so it's closed under the inversion. Okay? Recall that a group G is a set equipped with a binary operation such that the identity element exists, inverses exist, and the said binary operation is associative. Okay, so with the group G, we have a subgroup. H is a subgroup of G if and only if it contains the identity and it is closed under multiplication of its elements and under inversion of its elements. Now, a way to check that H is a subgroup, so you actually don't need to check all these three conditions. You can check that that H is non-empty and H is closed under the operation if A and B are elements of H, then A, B inverse belongs to H. So if H is closed basically under this operation which takes A and B in H and sends it to A, B inverse, then H is a subgroup of G if it's non-empty. Okay, so it's kind of a useful property, but I guess, like personally, I'll typically just check the standard conditions for a subgroup, but it's interesting to know that there's an alternative condition you can check, which is a bit more succinct. Okay, so now moving on, I'll note some examples of subgroups. If you have a family of subgroups, then the intersection of that family is again a subgroup. Okay, so the intersection of any family of subgroups is a subgroup. The subgroup generated by an element of G. So let A belong to G, let A be an element of G. Then we define the set H to be the set of all integer powers of A, namely the set of all elements A to the power n, where n is an integer. This is a subgroup called the subgroup generated by A. Okay? And note that this is the smallest subgroup of G containing A. Alright, so now let G be a group and let S be a subset of G. The smallest subgroup of G containing S, namely the intersection of all subgroups containing S, the set S, is called the subgroup of G generated by the set S. And this set, the subgroup generated by the set S, again, the intersection of all subgroups containing S, or in other words, the smallest subgroup containing the set S, is precisely characterized by the following set. It is equal to the set of all products of the form S1 ... through Sn, where each element of said product is an element of S, or its inverse is an element of S. Okay, so essentially, we take every element of the set S, we form the set which includes all of the elements of S and all of their inverses, and then we take the closure of this set under multiplication, finite products of its elements, and this gives us the subgroup generated by S. So it's the set of the form S1 product all the way through Sn, where each of these S sub i's in the product are either elements of S or their inverses are elements of S. Okay? Alright, now we have a definition of a homomorphism. Okay, so again, we have a group homomorphism. This group homomorphism is just a map between groups which obeys single property, namely that it preserves the multiplication structure. Okay, so let me see if I can find the official definition here for you. I think I skipped it. Just to be precise. Okay, so it is any mapping from a group G to a group H which respects the multiplication structure, namely phi of AB. If A and B are elements of G, then phi of AB is equal to phi of A times phi of B. Okay, so phi sends the product of elements in G to the product of their images in H. that is called a group homomorphism. Okay? Note that the properties of group homomorphisms, it sends the identity to the identity. Okay, so a group homomorphism will always send the identity to the identity. If it sends inverses in G to the inverse of their images in H, so phi of G inverse is equal to phi of G inverse. Okay. And finally, if it is a bijective mapping, then it is called an isomorphism, and the inverse is also an isomorphism. Okay, so group homomorphisms automatically have a ton of structure inherited only from the fact that they respect the multiplication structure of the domain and codomain in such a special way. They automatically inherit a ton of structure from that singular fact. Okay, so with that definition in hand, we now define the image of phi, which is just the set theoretic image of phi as a mapping. This is a subset of H given by the set of all image. It's literally just the set theoretic definition of the image of phi in H, and we define the kernel of phi is the set of all elements of G which get mapped to 1. So the set of all elements in G such that phi of G is equal to 1, the identity element of H. So it's the pre-image of the identity element of H under the group homomorphism phi. That is the kernel of phi. Now, we have that the image of phi is a subgroup of H, and the kernel of phi is also a subgroup of G. Okay, so image of phi is a subgroup of H, and kernel of phi is a subgroup of G. Okay. Turns out that the kernel is not just a subgroup of G, it's in fact a normal subgroup of G. We'll get to that soon enough. Okay. So there's a theorem which states that a group homomorphism F from G to H is injective if and only if its kernel is trivial. So if and only if the kernel of F consists of just the identity element of G. Okay? So a group homomorphism is injective if and only if its kernel is trivial. Okay? Now an injective group homomorphism will automatically give an isomorphism from the group G, between the group G and the image of the injective group homomorphism. Okay? So if a group homomorphism is injective, then its image is isomorphic to the domain G of the group homomorphism. Now, injective group homomorphisms are also called monomorphisms. Okay? So we have another definition. An embedding of a group G into a group H is an injective group homomorphism from G to H. Okay, and it's denoted with this inclusion mapping arrow from manifolds. So an embedding of a group G into a group H is an injective group homomorphism from G to H. Okay. So we have the left cosets given a subgroup of G. So given a subgroup of G, the left coset of H in G, so H is the subgroup. The left coset of H in G is a subset of the form AH for some A within G. This is the set of all elements of the form A times H, where H is an element of H. Okay, so I guess I should be distinguishing my capital H's and lowercase h's. So I will say Okay, H is our subgroup, and the subset of the form AH is the set of elements of the set formed by elements of the form A times an element of H, basically. Okay, so the left coset is this of H and G. The left coset of H and G is the set of the form A times H, where H is an element of the subgroup H. Okay, so that's a left coset. It's a set of all, okay. If A is an element of G, the left coset AH is the set of AB such that B belongs to H. Okay. Similarly, the right coset is a subset HA, subset of G. It's a subset. It's not necessarily a subgroup. It's obviously not necessarily a subgroup, because it's not. It's actually not a subgroup because it doesn't contain the identity unless A already belonged to the set H. So, I mean the subgroup H. So the right coset is a subset HA. So H is the subgroup, A is the element of G. This is a subset HA, which is it's the set of elements of the form BA such that B belongs to H. Okay, so BA such that B belongs to H. Now, okay, so two left cosets either coincide or are disjoint, right? They either coincide or they're disjoint. And this is because if you look at two left cosets, they're equal. So let's look at the left coset AH and the left coset BH, where A and B are elements of the group G and H is a subgroup of G. Then these two left cosets either coincide or are disjoint. And one has that AH is equal to BH if and only if A inverse B belongs to H, or equivalently, B inverse A belongs to H. Okay? So if A inverse B belongs to H, then these cosets coincide. If that does not occur, then these cosets are disjoint. Okay? So, in particular, G is partitioned by its left cosets. Okay? So G is the disjoint union of the left cosets of H and G. Now, let me just repeat that. G is partitioned by its left cosets, i.e., G is the disjoint union of the left cosets of H and G. Our notation will be G over H. Okay? So G quotient H. I won't say quotient, I'll say G over H. Alright? And then when I denote when this later gets turned into a group, if H is a normal subgroup, this is going to get turned into a group, and I will use the notation G quotient H. But for now, I'm using the notation, verbal notation, G over H. So G over H is the set of all left cosets of H and G. So G over H is the set of all left cosets of H in G. So it's the set of all subsets of G of the form AH, where A is an element of G. G over H, set of left cosets of H in G. Similarly, this can be it's denoted with this forward slash, I believe, or is that a backslash? Let me just let's just see once and for all if this is a forward slash or a backslash. Let's see. I'm going to guess it's a forward slash. Yes, it's a forward slash. I was right. Okay, so it's denoted G forward slash H. G forward slash H. Now, H backslash G. H backslash G is the set of right cosets of H in G. So that's H backslash G. But we're not going to be dealing with right cosets. We're going to be looking at left cosets. So we have a definition. Consider a subgroup H of G. Then the order of H in G, denoted by this G semicolon H, or G colon H, excuse me, G colon H in brackets. So the order of H and G is the cardinality of the set G over H, okay? So it is the cardinality of the set G over H. Namely, it is the number of left cosets of H in G. So this is the order of H in G, or also called the index of H in G. And it is denoted G colon H. G colon H in brackets. So bracket, like square brackets containing G colon H. This is the order of H in G, or the index of H in G, and it is the cardinality of the set G over H. Or in other words, it is the number of left cosets of H in G. Now, since G is partitioned by its left cosets, so G is the disjoint union of its left cosets, we obtain the theorem by Lagrange, namely that the cardinality of G is equal to the cardinality of H times the order of H in G. Okay, so that is the cardinality of the group G is equal to the cardinality of the group H times the number of left cosets of H in G. And that's written absolute value of G is equal to absolute value of H times G colon H in square brackets. Okay? All right. Now, as a corollary to this Lagrange's theorem, we have that the order of every subgroup of G divides the order of G. Okay, so, excuse me, when I say order, yeah, these notes are not fully consistent. So, right, so let me just repeat that corollary. Let's just start over with that corollary. Corollary of Lagrange's theorem is that the cardinality of every subgroup of G divides the cardinality of G. Okay? So, yeah, if H is a subgroup of G, its cardinality will divide the cardinality of G. Okay? And now, for any group element, okay, so I think we're using order. Sorry, I think we're using order. So the order of a group is given by its cardinality. And then we have this notation, the order of H in G. So the order of H in G is given by the index G colon H. So it's the cardinality of, yeah, the order of H in G is the cardinality of G over H. It's the cardinality of the number of left cosets of H in G. Okay, so moving on to our second corollary here, we have that for every element of G, the cardinality of the subgroup generated by this element divides the cardinality of G. So we define the order of an element. Let's call A to be an element of our group. We define the order of A to be the cardinality of the set, of the subgroup generated by A. Okay, so we look at the cardinality of the subgroup generated by A, namely the set of A to the power n, where n is an integer. We look at the cardinality of this subgroup generated by A. This is defined to be the order of A, and by Lagrange's theorem, the order of A will divide the order of G, will divide the cardinality of G. Okay. Right, then we are going to define normal subgroups and then take a break. So a subgroup H of a group G is called normal if its left cosets coincide with its right cosets. Okay, so a subgroup H in a group G is called normal if its left cosets coincide with its right cosets, i.e., for all A in G, for every element of our group G, we have that AH is equal to HA. So left coset of the left coset, let me see the right way to say this. Okay, I'm not sure how to say the left coset with respect to A, but I'll just say, okay, if A is an element of our group, we have that AH is equal to HA. So the left coset is AH, the right coset is HA. They coincide for all elements A of our group. Then the subgroup H is called normal. Okay? As an example, if the group G is abelian, if the overarching group G is abelian, then every subgroup is normal. Okay? And then we have an important proposition, namely that a subgroup H is normal in G. Subgroup H is normal in G if and only if H is closed under the conjugation, namely by G. Namely, we have that A inverse belongs to H for every A within G and H within H. Okay, so H is a normal subgroup of G if and only if it is closed under conjugation by elements of G, of the overarching group G. So if I take an element of H and I conjugate it by an element of G, so I take B within H, conjugate it by A within G to get a new element A, B, A inverse, then this new element remains in H. Okay? So we have closure under the conjugation by any element of G. Okay. Okay. Yeah, and this normal subgroup is denoted with a triangle inequality. So instead of just a subgroup, which is like a strictly less than symbol, one writes the strictly less than symbol with a vertical bar to make it into a triangle, basically. And this is the notation for normal subgroups. But I'll just say my verbal notation will just be H is a normal subgroup of G. So there shouldn't be any confusion there. We have that, H is a normal subgroup if its left cosets coincide with its right cosets, or equivalently, H is a normal subgroup of G if and only if for every B within H and for every A within G, we have that A, B, A inverse belongs to H. So H, the subgroup H, is closed under conjugation by any element of G. Now, later on we're going to talk about the normalizer, and the normalizer of a subgroup is going to be the stabilizer of the subgroup with respect to the group action given by conjugation. Okay? So, in this case, the group action by conjugation sends subgroups to subgroups, because if you take a subgroup and you conjugate it by an element of the group, so if you take H and send it to AH A inverse, this remains a subgroup. So you can use this to define a group action, the action of conjugation on the set of subgroups of G. And the stabilizer, given a subgroup H, the stabilizer of that subgroup with respect to this action of conjugation is called the normalizer of this subgroup. And so if H is a normal subgroup, then its normalizer is the entire group G, right? So if H is a normal subgroup of G, then its normalizer, namely its stabilizer under this conjugation action, is given by the entire group G. So it's normalized by, we would say that H is normalized by G, or the normalizer of H is the entire group G. Okay, and then the final proposition that I will mention is that given a group homomorphism F from G to H, the kernel of the group homomorphism is a normal subgroup of G. It is a normal subgroup of G. Okay? That follows from basically looking at F of GA, G inverse. This is F of G, F of A, F of G inverse. But by assumption, if A belongs to the kernel of F, then the image of A is 1 in H. And so F of A is equal to 1, and we just end up with F of G times F of G inverse, which is 1. So we get that the image, if the image of A is 1 in H, then the image of any conjugation of A by some group element G remains to be 1. So the kernel of the group homomorphism is a normal subgroup of the group G. This is always true. It's a very important property. Okay, so given a group homomorphism F from G to H, the kernel of F is a normal subgroup of the domain G. Okay, we're going to continue in a moment. I'm going to take a quick break. Okay, so returning to our summary, we just talked about how the kernel of a group homomorphism is a normal subgroup of the domain. And let's look quickly at an example. So, considering the kernel of the determinant homomorphism from GLNR or GLNC into R or C. Okay. if we look at the, so let's use K for the field, which could be the reals or the complex numbers essentially. Let's use K for the field. And then we have the determinant, which is a homomorphism from GLNK, equipped with the matrix multiplication, into K set minus 0, equipped with multiplication. So this is typically denoted K star or K cross. And this is a group homomorphism. Okay? By definition, we've removed matrices with determinant 0. So this is a group homomorphism, this determinant mapping, and the kernel is the preimage of 1, where 1 belongs to K cross, is the multiplicative identity. The preimage of 1 under the determinant mapping is the subgroup SLNK. SLNK, the set of matrices with determinant 1. But what we observe is that, in fact, SLNK is a normal subgroup of GLNK. Alright? SLNK is a normal subgroup of GLNK because it is the kernel of the determinant homomorphism. Okay, now, why is normality important? Well, one of the crucial reasons is that it allows us to put a group structure on the set of left cosets. Okay, so if let n be a normal subgroup of G, let n be a normal subgroup of G, then the product of two cosets is again a coset. Namely, if an and bn are cosets, here we have lowercase a capital N, lowercase b capital N. Okay, so I'm not going to say the lowercase and the uppercase, but when I use letters like N, G, and H, these are going to be subgroups. Typically, H is going to be a subgroup of G, N is going to be a normal subgroup of G, unless otherwise specified. These are denoted with capital letters, whereas elements of the form like A, B, C, D are going to be given lowercase letters. And then on paper, you can typically use elements like G and H in lowercase. But unfortunately, we don't have that freedom in the verbal setting. So I'm going to use letters like A, B, C, and D for group elements and reserve the letters G, H, and N for subgroups. Okay? So continuing with this proposition, I apologize for the digression. If N is a normal subgroup of G, then the product of two cosets is also a coset. So namely, we have that AN times BN, where AN and BN are cosets, AN times BN is equal to ABN. Okay? So we have AN times BN is equal to ABN. Okay? And this is, you can see that because you have that NB, the right coset, NB, is equal to the left coset, BN. Okay? So when we take the product as sets, okay, remember, the product as sets, AN times BN, of these left cosets, that product is defined, of sets, is defined to be the set of all products of elements of the sets. Okay? And the product of these two left cosets is again a left coset. AN, BN, AN times BN as a product of sets is equal to ABN. Alright? Now we have a definition. The quotient group. Okay? Also called the factor group. So because of this property, because normality allows the product of two cosets to again be a coset, we can make the set of left cosets into a group. So we can make, for n, if n is a normal subgroup of G, we can make G over n into a group which will be called G quotient n. G quotient n. And the group multiplication is just given by the multiplication of cosets as sets. Okay? So we have an, if an and bn are left cosets of G over n, then an times bn will be defined to be abn. And that equality is just also equivalent to setting the multiplication structure on G over n, the set of left cosets, to just be the set multiplication. So, namely, the product of two sets, as I said before, the product of two sets is just the set given by all elements of the form AB, where A belongs to the first set and B belongs to the second set. So we can define the product of sets in this manner, and then we have that the product of two left cosets is again a left coset, and the representatives of these left cosets, the representative of the product is the product of the representatives, the left cosets that we're multiplying. So that's the formula an times bn is equal to abn. And so we have that if n is a normal subgroup of G, then this multiplication structure is well defined, and we can turn this set of left cosets, G over n, into a group, G quotient n, called the quotient group of G by n. It's called the quotient group of G by n. Again, n needs to be normal in order for this multiplication of left cosets to be well defined. And we obtain a group homomorphism, a natural mapping, which sends every element of G to its corresponding left coset in G over n, or G quotient n. So namely, we send an element A to the left coset an. This natural mapping, which sends an element to its corresponding left coset, is a surjective group homomorphism, i.e. an epimorphism, is a surjective group homomorphism called the quotient homomorphism. Okay? So we have the quotient homomorphism, which is a natural mapping which sends G into the quotient of G by n, which sends an element of G to its equivalence class with respect to this quotient, namely it sends an element A to a left coset an. Okay, this is the quotient homomorphism. Okay, so I don't know if I already said this, but we need n to be a normal subgroup of G in order for the quotient group to be well defined. I know I already said it several times, but I want to emphasize that, okay? All right, now we have a correspondence theorem. Given a normal subgroup n of G, there is a natural bijection between the two following sets. The subgroups in G containing n and the subgroups of G quotient n, okay? So basically, any subgroup in G which contains n, if we look at its image under the quotient homomorphism, this will be a subgroup in G quotient n. And similarly, any subgroup of G quotient n can be made into a subgroup of G containing n by taking the preimage, the set theoretic preimage of the subgroup of G in G quotient n under the quotient homomorphism map. Okay? So this is called the correspondence theorem. It states that for n, a normal subgroup of G, there is a natural bijection between the two following sets. We have on one hand the subgroups of G which contain n, and on the other hand we have the subgroups of G quotient n. And there is a bijection between these two sets given by essentially the quotient homomorphism and its set theoretic inverse. Okay? All right, so now we move on to the isomorphism theorems. Okay, first, we need a definition. Factoring a homomorphism through a quotient. Given a group homomorphism F from G to H, and given a normal subgroup of G, N, so given N a normal subgroup of G, we say that F factors through the quotient G quotient N if there exists a homomorphism F tilde from G quotient N into H, such that F tilde composed with the quotient homomorphism is equal to F. So namely F is equal to F tilde composed with pi, where pi is the quotient homomorphism. Okay? And this can be represented by a triangle diagram where we have G going into H, and we have an arrow represented by the homomorphism F. We have G descending to G quotient N by pi. So we have G descending to G quotient N by the quotient homomorphism pi. And then we want the existence of an arrow from G quotient N into H such that the triangle will commute. Okay? And the key condition that we need to factor F through the quotient is that F must be constant on the fibers of the quotient homomorphism. Okay, so the fibers of the quotient homomorphism is just pi inverse of A for every A within G quotient N. And if F is constant along these fibers, then it will factor through the quotient. Okay, and this F tilde from G quotient N into H will be well defined. Now, this condition in a group theoretic sense is the following. F will factor through G quotient N if and only if the kernel of F contains N. Okay, so the kernel of F needs to contain the normal subgroup N. If the kernel of F contains the normal subgroup N, then G will factor through the quotient, and we can basically get a map F tilde from G quotient N into H, such that F is equal to F tilde composed with pi. Alright? So, if the kernel of F contains the normal subgroup N, then we're going to have basically that F is constant along the fibers of the quotient homomorphism, and so it's going to factor through the quotient. All right? Okay, now I will be back. Let's take a quick break. Okay, so now we begin with the isomorphism theorems. Okay? So the first isomorphism theorem is the following. Let F from G to H be a group homomorphism. Then F induces an isomorphism of G quotient kernel of F with the image of F. So we have that for any group homomorphism F from G to H, G quotient, the kernel of F, is isomorphic to the image of F. Now note the key property that this kernel of F is always a normal subgroup of G. And so this quotient group, G quotiented by the kernel of F, makes sense. Okay? And this first isomorphism theorem follows directly from the discussion of factoring through the quotient. Okay? So namely, we have that the group homomorphism F restricted to its image. So F as a group homomorphism from G to the image of F in H is automatically surjective if we restrict to its image, and then we just factor this through the normal subgroup given by the kernel of F, and this will induce an isomorphism because factoring through the kernel will make the map injective. Okay, so That's the first isomorphism theorem. It states that for any group homomorphism F from G to H, we have an isomorphism between G quotiented by the kernel of F and the image of F. These groups are isomorphic. The isomorphism is given by the basically restrict F to its image. So restrict F, basically view F as a map from G to the image of F, and then factor that mapping through the quotient, through the quotient G quotiented by the kernel of F. Okay? So, in particular, if the group homomorphism F from G to H is an epimorphism, i.e. it's a surjective homomorphism, then it induces an isomorphism between H and G quotiented the kernel of F. So we have G quotiented the kernel of F is isomorphic to H if F is an epimorphism. Okay? Alright, now I'll just look at a quick example here. We can prove the classification of cyclic groups given a cyclic group G and some generator. Namely, a cyclic group is any group with a generator. Let A be the generator of the cyclic group G. Then we can look at the homomorphism F from the integers into G, which sends the integer n into a to the power n. This is a surjective homomorphism by assumption, and we invoke the first isomorphism theorem to say that G is isomorphic to Z quotiented by the kernel of this F. But then the kernel of F is a subgroup of the integers. So it has to be of the form mz, right? It has to be of the form mz for some integer m, or it's trivial. But in either of these cases, we're going to get that G is isomorphic to Z mod mz, or just Z itself. Okay, so that's a nice example. Now let's move on to the second isomorphism theorem. Okay, so the second isomorphism theorem, let G be a group, let K be a subgroup of G, and let N be a normal subgroup of G. Then, Kn is a subgroup of G. N is a normal subgroup of Kn. K intersect N is a normal subgroup of K. And finally, the key statement of the theorem, Kn quotiented by N is isomorphic to K quotiented by K intersect N. Okay? So, let's just state this one more time. The second isomorphism theorem. Let G be a group, and let K be a subgroup of G, and let N be a normal subgroup of G. Then we have that Kn is a subgroup of G. N is a normal subgroup of Kn. K intersect N is a normal subgroup of K. And finally, the key statement of the theorem, Kn quotiented by N is isomorphic to K quotiented by K intersect N. Okay, so let me just state the key result. Again, K is a subgroup of G and N is a normal subgroup of G. Then Kn quotiented by N is isomorphic to K quotiented by K intersect N. Okay. And so basically the proof goes as follows. We first show that Kn is a subgroup of G, given that N is normal, and K and N are both subgroups. then we show that, okay, n is obviously normal in Kn because n is normal in G. We show that K intersect n is normal in K. So basically K belongs to the normalizer of K intersect n. And once these facts are shown, then the quotients in the key statement of the second isomorphism theorem make sense. So Kn quotiented by n makes sense, and K quotiented K intersect n makes sense. And so we can consider the following embedding. We can consider the inclusion of K into Kn. So consider the inclusion of K into Kn, and then compose that with the projection map, with the quotient map. Kn gets sent to Kn quotiented by n. Okay, so we have a composition of group homomorphisms. First, we have the inclusion from K into Kn. From the subgroup K into the subgroup Kn. Then we have the quotient homomorphism, which sends Kn to the quotient Kn by n, so Kn over n. We compose these two group homomorphisms and then look at the kernel. So it's surjective. We first show that this is surjective, and then we look at the kernel, and the kernel is K intersect n, and so we just use the first isomorphism theorem to conclude that K quotiented by K intersect n is isomorphic to Kn quotiented by n. Okay. All right. And then we have the third isomorphism theorem. So let's move on to the third isomorphism theorem. We have given two normal subgroups K and H. So now assume that K and H are normal subgroups with K contained inside of H. So K is a subgroup of H, and both are normal in G. One has that H quotiented by K, so H over K, embeds into G over K, so G quotiented by K. I'm actually just going to use the over notation, like H over K, to denote H quotiented by K, since it's more efficient over voice. So we have, okay, starting again, we have two normal subgroups K and H, with K contained inside H. So K is a subgroup of H. Then we have that H over K embeds into G over K. So we can define this inclusion mapping. H over K includes into G over K. And further, H over K is normal in G over K. So H over K is normal in G over K. And then the key result, which is the central statement of the third isomorphism theorem, is that G over K quotiented by H over K is isomorphic to G quotiented by H. Okay, so G over K quotiented by H over K is isomorphic to G quotiented by H. And that's written, basically it's like if you were to write A over B divided by C over B and say that's equal to A over C in fractions. We have that for groups. If K and H are normal in G and K is a subgroup of H, then we have that G over K quotiented by H over K is isomorphic to G quotiented by H. Okay? Now let me just quickly describe the idea of the proof. It's a similar idea. We construct the right surjective group homomorphism and then examine the kernel. So the group homomorphism we want to consider is the group homomorphism which sends G into G quotiented by K into G over K quotiented by H over K. And this composition can be shown to be surjective with kernel H. So we use the first isomorphism theorem. So we just compose two quotient maps. First we quotient by k, so we take g, send it to g over k, and then we look at the quotient map g over k quotiented by h over k. And we compose these two quotient maps, show that the composition is obviously surjective, but show that the kernel of this composition is the group H. So we get, by the first isomorphism theorem, we get g over k quotiented by h over k is isomorphic to g over h, or g quotiented by h. Now remember, we needed that both k and h are normal, and we needed that k is contained inside of h. Okay? And the key point to understand about this third isomorphism theorem is that this is really a way to simplify the quotient g quotiented by h as a quotient of smaller groups. G over k and h over k are smaller groups, and we're quotienting those instead. So we're taking g over k quotiented by h over k. So if we can find this normal subgroup K, a normal subgroup K in G, which sits inside of H, then we can simplify the quotient G over H as a quotient of smaller groups, G over K quotiented by H over K. Okay, so next section is on group actions, and yes, we will cover that in the next note. Okay, so now we move on to group actions. So let G be a group and let X be a set. An action of G on X is a map from G cross X into X, which sends a pair G comma X into an element of X denoted Gx. So it sends a pair G comma X into Gx. We're going to denote this group action mapping by theta. And the way to think about this group action, let me state the two axioms that this mapping theta must satisfy. So first, we require that 1x is equal to x for all x within x. So 1 comma x gets mapped to x for all x in x. And the second requirement is associativity, namely, if we have g of hx, then this is equal to gh times x. Okay, so right. So the way you can think of this is that if I apply theta of g comma x, so let's write g of hx is equal to gh times x. This is like saying theta of g comma theta of h comma x is equal to theta of gh comma x. Okay, so we have the associativity. But these are better thought of in the context of group homomorphisms. So we can view theta as essentially, we can view the group action as sending the group G into S of X, the set of permutations of X, set of bijections from the set X to itself. By basically every group element of G gets associated to a map, theta sub G, let's say. Theta sub G, which is a mapping from X into itself. Okay? So In particular, we have a group action induces a group homomorphism from G into S of X, the set of permutations of X. Okay. Now, I should recognize when I'm using letters G and H here, I should probably be using the letters A and B. So, yeah, I apologize. I was using the letters G and H as lowercase letters. And yeah, let me just restate the definition of group action with the correct verbal notation, because it's not really a problem to hear something twice. So we have the definition of a group action. Let G be a group, and let X be a set. An action of G on X is a map theta from G cross X into X, which sends the pair A comma X into AX, such that, first of all, 1x is equal to x for all x in X. So theta of 1 comma x is equal to x for all x within X. And the second property of the group action is associativity. For all A, B elements of our group G, and for all x within our set X, we have that A times BX is equal to AB times X. Okay? Or equivalently, we have that theta of A comma theta of B comma X is equal to theta of AB comma X. Okay, so this is the associativity. Now, let us proceed with a remark that there is a natural bijection between the set of actions of G on X, so the set of all actions of a group G on the set X, and the set of group homomorphisms from G into S of X, where S of X is the set of permutations of X. Okay, so this is a bijection of sets. On one hand side, we have the set of actions of G on the set X, and on the other hand, we have the set of all group homomorphisms from G into S of X, the set of permutations of X. Okay, and this bijection is as follows. We take a group action theta, which is a map from G cross X into X, which obeys the properties of the identity element and associativity. The identity element stabilizes every element of X. We take such a group action theta and we associate it to the group homomorphism, which sends A into theta sub A. Okay, so basically theta sub A is basically the map theta from X to itself, which sends X into AX. Okay, so theta sub A, we basically we fix an element of the group G and look at, okay, how does theta permute the elements of X for this fixed element A of our group. And this mapping, this permutation, or this bijection from X to itself is denoted theta sub A. So we basically fixed the first argument of theta to be A. And this is a bijection from the set X to itself, which we're going to denote theta sub A. And so we have that S of X, the set of permutations of X, is a group equipped with function composition, and the mapping from G into S of X, which sends A to theta sub A, is a group homomorphism. Now, this group homomorphism determines the group action in the sense that the set of all actions of the group G on the set X is in bijection with the set of group homomorphisms from G into S of X. Okay, so now we proceed with a definition. Let F from G into H be a group homomorphism. Assume that the group H acts on a set X. Then we get an action of G on X, called the pullback of the action of H along the group homomorphism F, defined by the map from G cross X into X, which sends A, X to F of A, X. So F of A, X. In particular, viewed from the lens of a group homomorphism from G into S of X, we define theta, we define the group homomorphism from G into S of X to be A maps to theta sub F of A, right? F of A, theta sub F of A, because F of A is an element of H, and we already have an action theta. Theta is the action of H on X. And so if we send an element A of G to theta sub F of A, we get an action of G on the set X. And this action is called the pullback of the action of H along the group homomorphism F. Okay, so we continue with a couple of remarks. So first of all, this axiom that theta sub 1 is the identity, or the axiom 1 times x is equal to x for all x and x. This guarantees that theta sub g is always a bijection with inverse theta sub g inverse, okay? So we can use the associativity and the fact that theta sub 1 is the identity map to guarantee that theta sub g is a bijection for all g within G with inverse given by theta sub G inverse. Now, second remark, any group action of any group action of any group G on any set X is the pullback of the standard action of S of X on X along the homomorphism G into S of X given by theta. This means that the action of S of X on X is universal. What is the action of S of X on X? Well, we take A, X, where A is now a permutation of X. We take A, X into A of X, if A is a permutation of X. So S of X has a natural action on X, given by you just send the element of S of X, X to the image of X under this element of S of X. This action of S of X on X is universal in the sense that any group action of any group G on any set X is the pullback of the standard action of S of X on X along the homomorphism F, which sends G into S of X, given by theta. Okay? So this is just kind of a structural remark, which is kind of similar to the fact that these group actions are determined by the corresponding homomorphism from G into S of X. Okay, so now we have a definition. Given an action theta from G cross X into X, we define the kernel of the group action theta as the kernel of the corresponding group homomorphism from G into S of X. So it's the kernel of the corresponding group homomorphism from G into S of X. Namely, this is the set of all G within G. This is the set of all, this is the set of all A within G, such that theta sub A is equal to the identity. Okay, so it's the set of all elements of our group such that the corresponding bijection, theta sub A, is the identity on X. Okay, and so this is the kernel of the group homomorphism from G into S of X determined by the group action theta. Now, the action theta is called faithful if its kernel is trivial. Okay? So in particular, so the action theta is called faithful if the kernel of theta is the identity. So in particular, for a faithful action theta, if A is not equal to 1, then theta sub A moves at least one element of X. So there exists an X such that theta sub A of X is not equal to X. I'm sorry, I'm using X in lower script and capital script. I'm saying X for elements of X, and I'm saying X for the set X. So I'll try to avoid doing that, but let me think about that, and I will be back. Alright, so let's continue. Given a group action theta, which is a mapping from G cross X into X, we define the kernel of theta to be the kernel of the corresponding group homomorphism from G into S of X. Namely, this is the set of G within G such that theta sub G is equal to the identity mapping from X to itself. So this is the set of G within G such that theta sub G is equal to the identity on X. The action theta is called faithful if its kernel is trivial. Okay, so namely, if its kernel is trivial, meaning that essentially if G is not the identity, then theta sub G has to move at least one element of X. Now we proceed with some further definitions. So let G act on a set X. For an element X in X, the orbit of X, denoted orb of X, is the subset theta sub G of X such that G is in G. It's the set of all images of X under some group element G. It's the set of all theta sub G of X such that G is in G. Okay, so it's basically the orbit of X is the set of all points in X which can be reached starting at X and via some group action, via basically some permutation of the set X induced by the group action. So namely, it's the set of all, you could write the set of all Gx such that G is in G, right? This is the orbit of the element X. As we discussed before, we're using lowercase x for elements of capital X, the set, and hopefully the context will make the uppercase versus lowercase clear. Now, again, let X be an element of the set X. The stabilizer of X, denoted stab of X, is the set of all G within G, such that Gx is equal to X. Namely, this is the set of all group elements G, such that the corresponding permutation, theta sub G, fixes X. So we have, again, the stabilizer of X is equal to the set of G within G, such that theta sub g of x is equal to x. Now it turns out that this is in fact a subgroup of g. So the stabilizer of x is a subgroup of the group g. The orbit of x is a subset of x given by every possible image of x under the group action. Okay, so those are the orbits and the stabilizers. Okay, now notice that being in an orbit is an equivalence relation. So if y is in the orbit of x, then we have that y is equal to gx for some g. But then just take g inverse y is equal to x. So that means that x belongs to the orbit of y. So in particular, we get that the orbits of an element are actually equivalence classes, and the set x is partitioned by its orbits. Okay, so x is the disjoint union over the orbits of its elements. Okay. Furthermore, we have that the kernel of the group action theta, the kernel of the group action theta is the set of all g within g such that theta sub g is the identity. This is just the set of all g within g such that theta sub g fixes x for all x in g. So namely, g belongs to the stabilizer of x for all x in x. So that means that the kernel of theta is equal to the intersection over the set x, over all points of the set x, of the stabilizers of these points. So kernel of theta is equal to the intersection of x within x, the stabilizers of x. We proceed with a definition. An action is transitive if it has just one orbit. Okay? So what this means is the set x is equal to the orbit of any one of its elements. In other words, for any x and y in the set x, there exists a g within g such that gx is equal to y. So any two elements are connected via some no, I don't want to say group action, but by one of the permutations in S of x. So basically, we can find g such that theta sub g sends x to y for any 2 points x and y and x. Any 2 points are connected via some permutation which is in the image of the homomorphism from g into S of x given by the group action. Okay, so an action is transitive if it has just one orbit. Okay, next we have some examples, some crucial examples. We have the regular action of g on itself. The regular action of g on itself is just given by sending g comma x to gx, the product gx in the group G. Okay, so this is just left multiplication. That is the regular action. Proceeding forward, looking at this regular action, it is the action of a group G on itself by left translation. This action is transitive. There is only one, meaning that there is only one orbit. This action is faithful. So the kernel is trivial, i.e., the intersection over all points in X of the stabilizers. Here, X is the group G. So the intersection over G of the stabilizers of G. The intersection, let's say, the intersection over A within G of the stabilizers of A, stabilizer of A, is equal to 1. Okay, so this is quite easy to see. Left multiplication map is never left multiplication by G is never the identity unless G is 1. And in fact, this action is more than faithful. It is in fact free. Being free is stronger than faithful, meaning that actually the stabilizers of any element of G are all trivial subgroups. Okay, so the stabilizers of X are all equal to 1 for all X within X. Okay, right? If X is stabilized by the group action, then we have Gx is equal to X, which implies that G is equal to 1. So the stabilizers are all just the trivial group for any X in X. That means that the action is free. Okay, so the stabilizers are all trivial. In particular, if G is not 1, then the permutation theta sub G moves every element of X except for the identity. Or actually, no, it moves the identity too. Yeah, theta sub G moves everything, basically, unless G is 1. Okay, moving on. We have the action. Okay, so we have the left coset action by left translation. Given a subgroup H of G, G will act on the set of left cosets, G over H, by left translation. So we have the group action of left coset action by left translation, which sends G cross G over H to G over H. And the mapping is given by A, comma, BH gets mapped into ABH, right? So this is the left translation action on the left cosets of H and G. Okay. Now this action is transitive, namely the orbit of H is just the entire set G over H. The orbit of H is the entire set G over H. The kernel of the action, okay, is we can calculate the kernel of the action by looking at the intersection of the stabilizers of all points in the set. So let's calculate for a given point in the set, which in this case is a left coset. Let's look at its stabilizer with respect to this group action by left translation. The stabilizer is actually given by the stabilizer of, let's say, AH is in fact AHA inverse, because if we take AH and left translate it by some element B, let's say, and it's invariant under this left translation, we have BAH is equal to AH, then we must have that A inverse BA H is equal to H, or in other words, A inverse B A belongs to H. Okay? But this just means that B belongs to AHA inverse. So B must belong to AHA inverse if we have that B belongs to the stabilizer of AH. So in particular, we have that the stabilizer of a left coset, AH, under the group action by left translation, is just equal to the set AHA inverse. Using this, we can calculate the kernel by taking the intersection over A within G of the stabilizers of AH, and taking the intersection over all the stabilizers, this is the intersection over A within G of AHA inverse. This is actually a subgroup of G, and it is called the core of H. It is the largest subgroup of H, which is normal in G. Okay, so the kernel of this group action is of group action of left translation on the set of left cosets the stabilizer of an element, AH, is just AH A inverse. The kernel of the group action is therefore the intersection of the stabilizers, so it's the intersection over A within G of AH A inverse. This is a subgroup of H, and in fact it is the largest subgroup of H, which is normal in G. It is called the core of H. Okay, so next we have a definition. An automorphism of G is an isomorphism from G to itself. Now, the automorphism group, aut of G, is a group under functional composition. As an example, we will look at the automorphism group of the integers under addition. The automorphism group of the integers is given by two maps, left translation by 1 and left translation by -1. Or in other words, multiplication by 1 and multiplication by -1. This is just plus or minus the identity map, which is isomorphic to Z mod 2Z. So the reason for this is because an automorphism of a cyclic group must map generators to generators. Okay? So we look at the integers, Z, that is an infinite cyclic group. It has two generators, 1 and -1. Any automorphism must map generators to generators. Any automorphism of a cyclic group must map generators to generators. And so we get that the automorphism group of the integers is just plus or minus the identity map. Similarly, we can look at the automorphism group of Z modulo NZ. And this is going to be the set of left translation by A, where A is an element coprime to N. Okay, so the automorphism group of Z modulo NZ is just the set of left translation maps by A, where the GCD of A and N is 1. So basically left translate by any element of Z mod NZ, which is coprime to N. Okay? That is the automorphism groups. So again, the reason for this is that generators need to map to generators. Note also that the Euler function is the cardinality of the set of such A within the integers Z modulo NZ, the set of such A which are coprime to N. So it's the number of elements, number of integers coprime to N which are less than or equal to N. Okay? So that's the automorphism group of Z modulo NZ. Note here that these are automorphisms. They have to send the identity element to the identity element, but here 0 is the identity element, not 1. Okay, so 1 is a generator. 1 is not the identity element. 0 is the identity element here. Okay? Okay. So now we move on to the next critical example, which is the conjugation action of G on itself. Okay, so consider the group action G cross G going into G, which sends A comma G to AG A inverse. Okay, so basically theta sub A from G to G is the group automorphism given by the conjugation by A. All right. For every A within the group G, the associated permutation theta sub A from G to itself is the map given by conjugation by A. This is a group automorphism for every A, not just a permutation. All right. So therefore, in fact, this mapping from G into S of G, which sends A to theta sub A, is in fact a map into the automorphism group of G. So it's a map from G into aut G, which sends A, an element A of G, to theta sub A, which is an element of aut G given by the conjugation map conjugating by A. Okay? Now, for any x within G, the orbit of x is the set of all elements of G of the form Gx G inverse for all G within G. So the orbit of an element x is the set of all Gx G inverse such that G is in G. This is called the conjugacy class of x. So this is called the conjugacy class of x. Since G is partitioned by its orbits, we have that G is the disjoint union of its conjugacy classes. The conjugacy classes of x are just the orbits of x under this group action, which is the conjugation action of G on itself. And so we find that G is the disjoint union of its conjugacy classes. Let's look at the stabilizer of x under such a group action. The stabilizer of x is the set of G within G such that Gx G inverse is equal to x. This is precisely the set of G within G such that Gx is equal to xg. Or in other words, the stabilizer of x is the set of elements in G which commute with x. This is defined to be the centralizer of x in G. Okay, so we have the stabilizer of x under this conjugation action of G on itself is defined to be the centralizer of x. This is all of the group elements G, or I should say A maybe, all of the elements A and G such that AX A inverse is equal to x. This is the set of elements in G which commute with x. It's defined to be the centralizer of x. And again, this is a subgroup. The stabilizer of x is a subgroup of G. All right? So now looking at the kernel. The kernel of the group action theta is the intersection of the stabilizers. So it's the intersection over all stabilizers, which again is a subgroup because it's an intersection of a family of subgroups. So the kernel is automatically a subgroup. The kernel of theta is the intersection over all stabilizers, is basically the set of group elements G such that Gx G inverse is equal to x for all x in G, right? We're taking the intersection over x in G of the stabilizers of x. This is just the set of G within G such that Gx G inverse is equal to x for all x in G. Okay? So in particular, this is the set of elements of the group which commute with everything. Okay? And this is called the center of G. It's denoted Z of G. So the center of G, denoted Z of G, is the kernel of the conjugation action of G on itself. And this is just the set of elements of G which commute with every other element of G. Now the center, Z of G, is an abelian normal subgroup of G. The center is an abelian normal subgroup of G. Okay? We now have another definition. An automorphism of G is called inner if it coincides with a conjugation map X gets conjugated by some G. Okay, so an automorphism of G is inner if it coincides with the mapping X gets sent to Gx G inverse for some G within G. In particular, the set of inner automorphisms are basically the image of the group action theta. When we view theta, this conjugation action of G on itself, when we view this group action via conjugation as a homomorphism from G into S of G, or namely as a homomorphism from G into aught G, the image of this homomorphism, which defines the group action, is defined to be the set of inner automorphisms. So an automorphism is inner if it coincides with some conjugation mapping X gets sent to Gx G inverse for some G within G. Okay. So the set of inner automorphisms of G is a subgroup. It is quite literally the image of this group action in aught G. It's the image of this group action via conjugation in aught G. It is a subgroup, and it is isomorphic to G quotiented by its center. Okay, so the center of G, remember, the center of G, the set of all elements which commute with everything, center of G is the kernel of this group action by conjugation. And the set of inner automorphisms is the image of this group action when viewed as a homomorphism from G into aught G. And so by the first isomorphism theorem, we get a canonical isomorphism that the set of inner automorphisms of G is isomorphic to G quotiented by Z of G, or G quotiented by its center. Okay? All right, now we have another crucial example. This is the conjugation action on the set of subgroups. Okay? So we'll note that if H is a subgroup of G, then if I conjugate H by any group element, it remains a subgroup. So for any A within G, the set AH A inverse is in fact a subgroup of G, if H is a subgroup of G. Okay? So now we define the conjugation action on the set of subgroups. So let G be a group, and let X be the set given by the set of subgroups of G, so the set of all H, such that H is a subgroup of G. Then we define the conjugation action as a map from G cross X into X, which sends A comma H to AH A inverse. Okay, so theta sub A will just conjugate a subgroup now, a subgroup H, by the element A. Now for this group action, this conjugation action on the set of subgroups, the stabilizer of a subgroup H is the set of G within G such that GH G inverse is equal to H. Okay, so it's the set of all, I should say A maybe, the set of all elements A of the group such that AH A inverse is equal to H, so H is stabilized with respect to theta sub A. This is the stabilizer of H. It is called the normalizer of H. Okay, so it is called the normalizer of H. It's denoted N sub G of H. N sub G of H. So the normalizer is a subgroup of G, and in fact H is normal inside the normalizer of H. Okay, so the normalizer of H, it's a stabilizer of so the stabilizer of an element H of our set, remember the stabilizer is always a subgroup, so the specific stabilizer with respect to the conjugation action on the set of subgroups, the stabilizer of a subgroup H with respect to this conjugation action is called the normalizer of H. It consists of all elements of G such that GH G inverse is equal to H, or in particular conjugating H by this element G, or maybe I should say A, conjugating H by this element A gives you H again. Okay, this is the stabilizer of H. It's called the normalizer of H. The normalizer of H. And in fact, H is a normal subgroup of its normalizer. So H is a normal subgroup of its normalizer, which is a subgroup of G. In fact, the normalizer of H is the largest subgroup of G, such that H is normal inside it. Okay? So it's the largest subgroup of G such that H is normal inside of it. Okay? So basically, if H is normal inside any subgroup, then that subgroup must be contained in the normalizer. Right? So you can think of the normalizer as the set of all group elements, which basically, if you take an element of H and conjugate it by this group element, you remain inside of H, right? So H is stabilized with respect to this. For any element in the normalizer, the corresponding group homomorphism in this case, or not a group homomorphism, but the corresponding permutation, theta sub A, which sends the subgroup H to AH A inverse, theta sub A of H is equal to H, basically. Okay, so let's move on from this. Okay, so we're now going to move into some newer territory. Okay, so we begin by recalling a lemma. So let H be a subgroup of a finite group G. So let H be a subgroup of a finite group G, such that the order of H in G is the smallest prime divisor of the order of G. Okay. Then H is normal in G. Okay, so again, let's just repeat this lemma. Let H be a subgroup of a finite group G such that the order of H in G is the smallest prime divisor of the order of G. Then H is normal in G. Okay? This is an interesting lemma. The proof is also somewhat interesting. So we have that the order of H and G is, by Lagrange's theorem, or I guess by definition, it's the number of left cosets. It's the cardinality of the set of left cosets. So let's call this cardinality P, where P is the smallest prime divisor of the cardinality of G. Then our group action of G on the set of left cosets of H in G. Consider the group action by left translation on the set of left cosets. Okay, then this group action gives us a homomorphism from G into the set of permutations into the S of G over H, basically the permutation, the set of permutations, bijections from G over H to itself. The point is that we get this embedding from basically, this is a nice proof. The kernel of this group homomorphism. If we look at the group homomorphism given by the action of G on G over H via left translation, we look at its kernel. The kernel is the core of H. Okay, remember, the kernel of this group action is the core of H. This is the intersection over all the stabilizers of left cosets AH, which is the intersection over A within G of AH A inverse. Okay, we're going to define this to be N. Then we have a group embedding G quotiented by N into S of G over H. So G quotiented by N, the cardinality divides P factorial, because P factorial is the cardinality of this group S of G over H. And so we have this very crazy argument. We basically get that G quotiented by n, it's a subgroup of G, but it divides P factorial. It divides P factorial and it divides the order of G. Since P is the smallest prime divisor of G, we must have that the order of G quotiented by n is P. That's precisely the order of G over n. It's the number of left cosets of H and G. So we get that, in fact, H is equal to n, but since n is the kernel of the group action, it's a kernel of group homomorphism, we must have that H is normal. So, yeah, I don't think you really need to understand the detail. This is kind of a tricky proof. It's a very interesting proof, though. But it leads us, so we'll just move on for sake of time. We have the orbit stabilizer theorem, okay? So let me just repeat that past lemma because I made you sit through it. So the past lemma, let H be a subgroup of a finite group G such that the index of H in G, or the order of H in G, is the smallest prime divisor of the order of G. Then H is normal in G. Okay, moving on, we have the orbit stabilizer theorem. Now this is important. The orbit stabilizer theorem. Suppose we have a group action G acting on a set X. Let X be an element of the set X. Then, the cardinality of the orbit of X is equal to the cardinality of G over the stabilizer of X. In particular, if G is a finite group, then the cardinality of the orbit of X is equal to the cardinality of the group G divided by the cardinality of the stabilizer of X. Okay? And this is because, so the reason for this theorem, which is called the orbit stabilizer theorem, it can also be stated for, basically for, remember, okay, let me just explain something. Stabilizer of X is a subgroup, okay? So for every X with an X, the stabilizer of X is a subgroup of G, set of all elements of G which fix X. So we can consider the set of left cosets of the stabilizer of X in G. The cardinality of this set of left cosets of the stabilizer of X, which is a subgroup of G, is equal to the cardinality of the orbit of X. The orbit of X is a subset of X, okay? But basically, the cardinality of the orbit of X is equal to the cardinality of the set of left cosets of the stabilizer of X in G. And then if G is a finite group, we have that the cardinality of the orbit of X times the cardinality of the stabilizer of X is equal to the cardinality of G. Okay, and the proof basically boils down to saying that we can look at a surjective map of sets which sends a group element G to the element of the orbit of X, namely theta sub G of X. So we should say a surjective map of sets which sends a group element A to theta sub A of X, which belongs to the orbit of X. And then the point is that if we look at if two elements of the group A and B get sent to the same image point, we would have that theta sub A of X is equal to theta sub B of X. This can only hold if, we have AX is equal to BX, but then we must have that basically A inverse BX is equal to X, so X is equal to A inverse BX. But that implies that A inverse B belongs to the stabilizer of X. So we have that the left coset A times the stabilizer of X is equal to the left coset B times the stabilizer of X. Okay? So basically, using this, we can say, okay, this surjective map of sets, which sends A into theta sub A of x, if you look at the fibers are just going to be the left cosets of the stabilizer of x. So we get a bijection of sets between the left cosets of the stabilizer of x and G with the orbit of x. Okay, and we will return in a moment. Okay, so let us proceed with an example of an application of the orbit stabilizer theorem. We have that for a finite group G and a subgroup H of G, the number of subgroups in G which are conjugate to H is equal to the index of the normalizer of H in G. Why is this the case? Well, the normalizer of H in G is the stabilizer of H with respect to the action of conjugation on the set of subgroups of G. So we have that the number of subgroups in G which are conjugate to H is simply the orbit of H under this group action of conjugation on the set of subgroups of G. And so by Lagrange's theorem, since the normalizer of H with respect to this group action is just the stabilizer of H, we have that the index of the normalizer of H in G is equal to the cardinality of G divided by the cardinality of the normalizer of H. But then applying the orbit stabilizer theorem, this is exactly the orbit stabilizer theorem with respect to this group action, right? We have that the cardinality of the orbit of H, which is just the number of subgroups in G which are conjugate to H, is equal to the cardinality of G divided by the cardinality of the stabilizer of H, which is precisely the normalizer of H. So we get that the cardinality of the orbit of H under this group action of conjugation on the set of subgroups is precisely equal to the index of the normalizer of H in G. Okay, now we have a definition, fixed points, okay? Let G act on a set X. Let S be a subset of G. Then the set X superscript X, the set X superscript S. The set X superscript S is defined to be the set of points in X fixed by S, okay? So the set of points in X fixed by S. Namely, this is the set of X within X such that Sx equals X for all S within S. Okay, so the set X superscript S of points in X which are fixed by the entire set X with respect to this group action, where S is a subgroup, not a subgroup, S is a subset. S is a subset of the group G. But it turns out that the set of points in X fixed by S is the same set as the set of points in X fixed by the subgroup generated by the set S. So recall the subgroup generated by the set S is basically the intersection over all subgroups containing S. Then the set of fixed points with respect to that subgroup generated by S is the same as the set of points fixed by just the set S. Okay? All right, and then we mentioned Burnside's lemma. So given a finite group G, which acts on a set X, the number of orbits for this group action is equal to the average number of fixed points over G. Namely, the number of orbits for this action is equal to 1 divided by the cardinality of G, so 1 over cardinality of G, times the summation over all A within G of the cardinality of X superscript A. Okay? So we look at the fixed points with respect to some element G, or some element A, sorry. We look at the number of fixed points with respect to some element A of our group G. So this is the set of X within X such that AX is equal to X. Okay? Look at the number of fixed points with respect to the group element A, and then we sum over all group elements. We take the summation of the cardinality of these set of fixed points with respect to group element A. We take the summation of those cardinalities over all A and G, over all elements of the group, and then we divide by the cardinality of the group G itself, and this is equal to the number of orbits for the action. Okay, so Burnside's lemma essentially states that the number of orbits for a group action G acting on X, where G is a finite group, the number of orbits for the action is equal to the average number of fixed points over G. Okay, so the proof of this is quite beautiful, so I'll just quickly mention it, even though I shouldn't. So we look at the set of orbits. We look at the set of all orbits, and this is just the summation over X and X of 1 over the cardinality of the orbit of X, since X is partitioned by its orbits. Then we apply the stabilizer. So basically, it's like taking... we look at, okay, the orbits partition X. So the set of all orbits partition X. And so we can do this summation over all elements of X of 1 divided by the cardinality of the orbit of X. Okay, so then this summation, every time we're in one orbit, right, this summation, we're going to sum 1 over the cardinality of the orbit of X. We're basically summing that over the orbit of X. That's just going to give us 1. And then we sum that over all of X. We get the cardinality of the set of orbits. Okay? And then we apply the orbit stabilizer theorem to say, write this as the summation over X and X of the cardinality of the stabilizer of X divided by the cardinality of G. But this is just 1 over the cardinality of G times the summation of X within X times the summation over G within G of an indicator function Gx equals X. Okay, so summation over G within G of indicator function Gx equals X. This indicator function is 1 if G belongs to the stabilizer. And then we sum over all group elements G to get the cardinality of the stabilizer of X. And then we interchange these two sums to write this is equal to 1 over the cardinality of G times the summation over G within G, summation over X within X of the indicator function Gx equals X. The summation over X within X of the indicator Gx equals X, well, this indicator function that Gx is equal to X can also be viewed as being 1 if X belongs to this X superscript G, namely if X belongs to the set of points fixed by G. And so we get the summation over X within X becomes just the cardinality of the set of points in X fixed by the element G. And then we're taking the summation over all group elements G within G. So that's basically the structure of the proof, and that might have been too technical to put in a voice recording, but it's a really nice proof of Burnside's lemma, so I just wanted to briefly mention the proof because it is a really nice proof. So let's keep moving. Our next section is on Sylov's theorems. Sylov's theorems, okay? So we're going to be assuming that we have a finite group, okay? So everywhere here in this section, G is a finite group and P is a prime number. So P is a prime number and G is a finite group. So we begin with a definition. of a P group and a P subgroup. So we'll say that G is a P group if the cardinality of G is P to the power K for some K within N. So namely, if the cardinality of G, or the order of G, is equal to a prime number to some power. Okay? Now, for any group G, which is not necessarily a P group, any group G, a P subgroup of G is a subgroup H of G, which is itself a P group. So the cardinality of H is some power of P for a prime number P. Now we have a lemma. Let H be a P group acting on a finite set X. Then the set of points fixed by H, the entire P group H, the cardinality of this set of fixed points is equal to the cardinality of X modulo P. Okay? So the cardinality of X superscript H, which is equal to the set of points in X fixed by the entire group H, okay, by the entire group H with respect to this group action, is equivalent to the cardinality of X itself modulo P. This is because the reason for this lemma is because X is partitioned by its orbits, okay? So every orbit with more than one element, remember, by the orbit stabilizer theorem, if we take an orbit with more than one element, okay, then this orbit, okay, has cardinality given by the cardinality of H divided by the cardinality of the stabilizer of some element in the orbit, right? In particular, the cardinality of the orbit must divide the cardinality of H. But since H is a P group, this means that the cardinality of the orbit must have that P divides this cardinality, right? The cardinality of the orbit must have some prime factor P, okay? So then, if X is partitioned by its orbits, then every orbit with more than one element, for the reason we just discussed, every orbit with more than one element has that P is a divisor of the cardinality of this orbit. And so if we write X as the disjoint union over all its orbits, then we see that every element of this disjoint union with more than one element, every orbit with more than one element will have cardinality which is equal to 0 mod P. And so the only remaining points are basically the orbits with one element, namely the fixed points of the group action. And the fixed points, therefore, the set of fixed points, X superscript H, is equivalent to X modulo P in cardinality. So the cardinality set of fixed points is equal to the cardinality of X itself modulo P. Okay. Now we have a critical theorem. This is Cauchy's theorem. Okay? If G is a group, okay? If G is a group, any group, such that P divides its order, so P is a divisor of the cardinality of G, then G contains an element of order P. So let me repeat this theorem by Cauchy. If P divides the cardinality of G for any group G, then G contains an element of order P. Okay, so the proof of this theorem is somewhat technical. It's a crazy, crazy proof. Should I include it or not? Okay, whatever. Let's just mention some of the ideas from it. I would be ashamed not to mention some of the ideas from this proof. So we're going to consider the set X, which is basically we're going to look at the the p-fold product of G with itself. So look at G cross G cross G, etc. Look at the direct product of G with itself, p times. Then look at the mapping, look at the homomorphism, or not homomorphism, but just look at the map which takes an element of this direct product into G, which sends, this is not actually, I don't know if this is a group homomorphism, but look at basically the map which sends the p-fold product of G with itself into G, just given by taking the product. If you take x1 comma dot 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 comma xp, that gets mapped to the product x1 times x2 dot 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 times xp. All right, and then look at the preimage of 1 under this map. That's going to be our set X. Okay, and notice that the set X has cardinality 0 modulo p, because its cardinality is essentially equal to the cardinality of G to the power p minus 1. Because if x1 dot 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 xp gets sent to 1, then you must have that xp is equal to the product of x1 with xp minus 1, x1, x2 dot 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 xp minus 1 inverse. Okay, so we get that this cardinality of the set X is equal to 0 mod p. And then we do the group action of cyclic permutation. Okay, so we do this group action. H is a group of order p with this is crazy. This is a crazy proof. Okay, so we basically permute the elements. We consider this group action which permutes elements, so namely sigma of x1 dot 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 xp, x1 comma dot 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 comma xp gets sent to x2 comma dot 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 comma xp comma x1. Okay, and basically we apply this lemma that the cardinality of the set of fixed points is equal to the cardinality of x modulo p, so namely the set of fixed points is 0 modulo p. But the set of fixed points under this group action is just the set of elements of order p. Okay, so since this set of fixed points has cardinality greater than or equal to 1 and it's divisible by p, we must have some non-trivial element that gets fixed by this group action. And this non-trivial element is precisely an element of order p. So I suggest that this proof is probably too technical at my current level in algebra to put on a voice recording. But let's just repeat the theorem by Cauchy that if a prime p divides the order of G, then G contains an element of order p. Okay, now we're going to move on to the next theorem, which states that every non-trivial p group has non-trivial center. All right? Every non-trivial p group has non-trivial center. I'm going to basically skip the proof because these proofs are going to get too technical for me at my current level to put on a voice recording. Okay? So we'll just state this theorem. Every non-trivial p group has non-trivial center. I hate skipping proofs, but debating if I should state the proof. Okay, actually the proof is somewhat straightforward, so let's just state the proof. Let G act on itself by conjugation. Then the center of G is the fixed points x superscript G of this group action. So by the lemma, we have that the cardinality of the center, which is the cardinality of x superscript G, is just equivalent to the cardinality of x modulo p. But G is a p group. So x is equal to G, it's a p group, so it's equal to 0 mod p, which means that the cardinality of the center is 0 mod p. but one belongs to the center. So, the cardinality of the center must be greater than or equal to P. In particular, the center of G is non-trivial. Okay, let's mention another crucial lemma. Let H be a P subgroup of a finite group G. Let H be a P subgroup of a finite group G. Then the index of H in its normalizer, so the index of H in the normalizer of H, is equivalent to the index of H in G modulo P. Okay? So the index of H in its normalizer is equivalent to the index of H in G modulo P, when H is a P subgroup of a finite group G. Okay, and for this proof, we consider the let H act on the set of left cosets G over H by left multiplication, by left translation. So let H act on the set of left cosets of H and G by left translation. Then you can calculate that the set of fixed points X superscript H, so points that are fixed by every element of H, okay, is precisely the index of H in its normalizer. The index of H in its normalizer, okay? Because if a left coset GH is fixed by this left multiplication, we must have that, or sorry, if the left coset, let's say AH, is fixed by this action of left multiplication by H, we must have that A belongs to the normalizer of H. And so in particular, we have that the cardinality of the set of fixed points is equal to the index of H in its normalizer. And then we apply this lemma, this crucial lemma, that the cardinality of X to the power H, so set of fixed points fixed by every element of the group action, is equivalent to the cardinality of X modulo P. But the cardinality of X is just the index of H in G. Okay? So we get that the index of H in its normalizer is equivalent to the index of H in G modulo P. Now we used the fact that H is a P group. Where did we use this fact? Because the group, so remember for this lemma, we have that H needs to be a P group acting on a finite set X. H has to be a P group acting on a finite set X to get the lemma that the cardinality of the set of fixed points X superscript H is equivalent to the cardinality of X modulo P. Okay? So now we have a new definition, a P-C-Love subgroup. Okay? So a P-C-Love subgroup. We're going to write the cardinality of G is equal to P to the n times m, where P does not divide m. Okay, so we consider, basically, we pull out all factors of P from the cardinality of G. And we write cardinality of G is equal to P to the power n times m, where P does not divide m. Then a P-C-Love subgroup of G is a subgroup of order P to the power n. Okay? So a P-C-Love subgroup of G is a subgroup of order P to the power n, where P to the power n is basically the n is the amount of, is basically the degree of P which divides, maximal degree of P which divides the cardinality of G. Okay? Alright, so when we return, we're going to discuss the C-Love theorems. Okay, so let's look at the first C-Love theorem. Let G be a finite group, let P be a prime number, and let H be a P subgroup of G. So the cardinality of H is a power of P. Then, first, if H is not a P-Selov subgroup, then H is contained in a P subgroup of order P times the order of H, in which it is normal. So let me repeat that. If H is not a P-Selov subgroup, then H is contained in a P subgroup of order P times the order of H, in which it is normal. Secondly, H is contained in a P-Selov subgroup of G. Okay? So, in particular, G contains at least one P-Selov subgroup. Let's repeat the theorem one more time. This is the first Selov theorem. Let G be a finite group, P be a prime number. Let H be a P subgroup of G. Then, first, if H is not a P-Selov subgroup, then H is contained in a P subgroup of order P times the order of H, in which it is normal. Secondly, H is contained in a P-Selov subgroup of G. As a consequence, G contains at least one P-Selov subgroup. Okay, so the proof is important and we're going to include it. So we only need to prove the first statement. The second statement follows immediately from the first statement. So given a P subgroup H of G, which is not a P-Selov subgroup, then we know that the order of H is P to the K, where K is strictly less than N, where N is given by the prime factorization of the cardinality of G is equal to P to the power N times some other prime factors which are not equal to P. Okay, so P to the power N is basically the power of P, which the highest power of P, which shows up in the prime factorization of G. We have that the cardinality of H is P to the K, where K is strictly less than N, because H is not a P-Selov subgroup. So, in particular, the index of H in G is divisible by P, right? Because the index of H in G is just the cardinality of G divided by the cardinality of H by Lagrange's theorem. So this is divisible by P, because we've assumed that H is not a P-Selov subgroup. And by the previous lemma, we have that the index of H in its normalizer is equal to the index of H in G. So in particular, the index of H in its normalizer is equal to 0 mod P. Okay? So P divides the index of H in its normalizer. But the index of H in its normalizer is the set of left cosets of H, is equal to the cardinality of the set of left cosets of H in its normalizer. So in particular, since H is normal inside of its normalizer, we have that the set of left cosets of H in its normalizer is actually a group, namely the normalizer of H quotiented by H. This is a group, and its order is equal to the index of H in its normalizer, so this order is divisible by P. So by Cauchy's theorem, we can find an element in this quotient, normalizer of H quotiented by H. We can find an element in this group of order P. So there exists an X within normalizer of H quotiented by H, which is of order P. But then the subgroup generated by X, so X is of order P, the subgroup of this quotient group, normalizer of H quotiented by H, the subgroup of this quotient group generated by X is a subgroup of order P, since X is of order P. But then, if we look at the quotient homomorphism which sends the normalizer of H into the normalizer of H quotiented by H, we look at the inverse image under this quotient homomorphism of the subgroup generated by this X, this element of order P. We look at its inverse image under the quotient map. This is a subgroup of the normalizer, and H is basically a subgroup of pi inverse of this subgroup generated by X, which is a subgroup of the normalizer. So H is normal in this pre-image of the subgroup generated by X, the pre-image under the quotient homomorphism. So H is normal in pi inverse of the subgroup generated by X. And in particular, and also the order of pi inverse of this subgroup generated by X, the order is precisely the order of H times the order of the group generated by X, subgroup generated by X, which is just P times the order of H. So we have that pi inverse of this subgroup generated by X is the desired subgroup in G. Okay, so quite a bit of a technical proof, so it probably was hard to follow the details, but hopefully that covered the main picture. Let's move on to the second Sylow theorem. Okay, so this is the second Sylow theorem. Let H be a P subgroup of G. Let capital P, okay, now we're using capital P in the notes, so let's use a different letter. Let's use K. All right, so let H be a P subgroup of G, and let K be a P Sylow subgroup of G. Then there exists an A in G such that AH A inverse is a subgroup of K. All right, so given a P subgroup of G and a P Sylow subgroup of G, we can find an element of G such that the P subgroup conjugated by this element sits inside of the P Sylow subgroup. Okay? And the second part of this theorem, which is a direct consequence, states that any two P Sylow subgroups of G are conjugate. So any two P Sylow subgroups of G are conjugate. So let's restate the first part of this theorem. Given H a P subgroup of G, and given K a P Sylow subgroup of G, then there exists an element A in G such that AH A inverse is a subgroup of K. Namely, given any P subgroup and any P Sylow subgroup, there is an element of G such that the conjugation by this element of the P subgroup sits inside of the P Sylow subgroup. As a consequence, any two P Sylow subgroups of G are conjugate. Okay, so let's look at the proof. First of all, the first statement implies the second, just by an analysis of cardinality. The cardinality of the P subgroup conjugated by some element is just the cardinality of the P subgroup. And so if H is a P Sylow subgroup, then its cardinality must be equal to this the cardinality of the P Sylow subgroup K. And so in fact, these two P Sylow subgroups would be conjugate. So the second statement is already implied by the first, just by looking at the cardinality. The proof of the first claim is as follows. We're going to let H act on the set of left cosets of K in G, okay? So let H act on the set of left cosets of K in G by left translation. Then the set of fixed points of this group action, okay? So if x is the set of left cosets of k and g, then x to the power h in cardinality is equivalent to the cardinality of x modulo p, based on our crucial lemma, since H is a P group. Since H is a P subgroup, then if we consider the action by left translation, we have the cardinality of the fixed points of the whole group H is equal to the cardinality of the set X modulo P. Now the cardinality of the set X is the cardinality of the set of left cosets of K in P. But this is simply M, where the cardinality of G is given by P to the n times M, where M is not divisible by P. So the cardinality of this set of left cosets is this factor M, which is not divisible by P. And so in particular, we find the set of fixed points of this group action, namely the cardinality of x to the power h, is not equal to 0 mod P. In particular, there is a fixed point inside this set. In particular, there's a fixed point AK. There's a fixed point AK such that basically AK is fixed by any element of the group action. So in particular, we have that HAK is equal to AK. HAK is equal to AK, which implies that A inverse HA K is equal to K. So in particular, we must have that A inverse HA is a subgroup of K. All right, so that is the second Sylow theorem. A corollary to the second Sylow theorem is the following. Since any conjugate of a P-Sylow subgroup is also a P-Sylow subgroup, and the second part of the theorem tells us that any two P-Sylow subgroups are conjugate, we have that this following corollary, that G has exactly one P-Sylow subgroup if and only if G has a normal P-Sylow subgroup, okay? So if G has a normal P-Sylow subgroup, then it's fixed by this action of conjugation. So if you conjugate by any element, it will be fixed. And so there is no other P-Sylow subgroup that you can get to via conjugation. And so G must have just one P-Sylow subgroup, because any two P-Sylow subgroups are conjugate, okay? So let's just repeat the corollary, that G has exactly one P-Sylow subgroup if and only if G has a normal P-Sylow subgroup. Okay, so proceeding, we're now going to use some notation to state the third Sylow theorem. So the notation is the following. We're going to consider Sylow of G, which denoted SYL sub P of G, is the set of P-Sylow subgroups of G. So Sylow sub P of G is the set of P-Sylow subgroups of G, and let N sub P be equal to the cardinality of this set. So N sub P is basically the number of P-Sylow subgroups of G. Then the third Sylow theorem states that N sub P, if the cardinality of G is P to the N times M, where P does not divide M, then N sub P divides M, and N sub P is equivalent to 1 modulo P, okay? So the number of P-Sylow subgroups of G divides M and is equivalent to 1 mod P, okay? Where M is this remaining factor in the cardinality of G, namely, if we write the cardinality of G is P to the power N times M, where P does not divide M. Then, again, that's where the M is coming from. Then we have that the number of p-C-love subgroups of G divides M, and furthermore, the number of p-C-love subgroups of G is equivalent to 1 modulo P. Okay, so the proof, should we go through it? I keep debating if I should state the proof or skip it. Let's just go through the proof. So G will act by conjugation on the set of p-C-love subgroups of G. And this action is transitive by the second C-love theorem, because any two p-C-love subgroups are conjugate. Okay? So in particular, the orbit of any p-C-love subgroup is equal to this entire set of p-C-love subgroups under this action by conjugation. And so we have that n sub p, the number of p-C-love subgroups, n sub p, is equal to the cardinality of the set X, where X is equal to the set of p-C-love subgroups, which is equal to the cardinality of the orbit of K, where K is some element of X, some p-C-love subgroup. So the n sub p is equal to the cardinality of the orbit of K, which by the orbit stabilizer theorem is equal to the cardinality of G divided by the cardinality of the stabilizer of K. Now the stabilizer of K under this conjugation action is precisely the normalizer of K. All right? So since K is a subgroup of its normalizer, we have that the cardinality of G divided by the cardinality of the normalizer of K, this is going to divide the cardinality of G divided by the cardinality of K. And so in particular, n sub p, which is equal to the cardinality of G divided by the cardinality of the normalizer of K, divides the cardinality of G divided by the cardinality of K, which is precisely equal to M. So we have that n sub p divides M. That's the first part of the third C-love theorem. The second part, we're going to consider K, again, a p-C-love subgroup. We're going to let K act on the same set X, which is equal to the set of p-C-love subgroups. We're going to let K act by conjugation. Okay? So since K is a p-group, we have this lemma can be applied. So the set of fixed points, x to the power k, in cardinality is equivalent to the cardinality of x, which is equal to n sub p by definition. And this equivalence holds modulo p. So we have the cardinality of x to the power k, namely the set of fixed points, is equivalent to n sub p modulo p, where n sub p is just the cardinality of x. So now we look at the cardinality of the set of fixed points, and we argue in the following manner. If Q is an element of this set of fixed points, okay, then Q is a p-C-love subgroup which is fixed by every element of K. So in particular, AQ A inverse is equal to Q for all A within K. So in particular, we have that K must belong to the normalizer of Q. So K is a p-C-love subgroup of the normalizer of Q. But Q is also a p-C-love subgroup of the normalizer of Q. Q sits inside its normalizer. So both K and Q are p-C-love subgroups of the normalizer of Q. But Q is a normal subgroup of its normalizer. Q is a normal subgroup of its normalizer. So by the previous corollary from the second p-C-love theorem, we must have that K is equal to Q. And so the set of points x superscript K, set of fixed points, is just the singleton set K. K is the only element. K is the only p-C-love subgroup which is fixed by this action of conjugation by elements of K. And so the set of fixed points has cardinality 1, which tells us that 1 is equivalent to n sub p modulo p. Okay? So that is the third C-love theorem. now we are moving on to the next section. The next section is on direct products, and I'll see you there. Okay, so now we're talking about direct products. So we have a definition. Let G1 through Gn be groups. The direct product G1 times G2 times ... times Gn, or G1 cross G2 cross ... cross Gn, which is also called the external product, is basically the Cartesian product of these groups equipped with component-wise multiplication. Okay, so it's the Cartesian product of the groups equipped with the component-wise multiplication. This is the direct product of groups. Okay. Now we'll note that the cardinality of the direct product of these groups is just equal to the product of their cardinalities. Okay. So we'll also note that the direct product of abelian groups is abelian. We now define an internal direct product. So let G be a group, and let H1 through Hn be some subgroups of G. We say that G is the internal direct product of these subgroups H1, Hn, if the map given by H1 times ... times Hn, so the direct product of all these subgroups, the map into G given by taking an element H1, Hn and sending it to the product H1 times H2 ... times Hn in G. Okay, so taking an element of the direct product of the subgroup and sending it to the product of all of its components in G. If this map is a group isomorphism, then we say that G is an internal direct product of these subgroups. Okay, so we take some subgroups of G, we look at their direct product, we have a mapping which sends their direct product into G, given by taking all the components of an element of a direct product and multiplying them all together. If this mapping is a group isomorphism, so if this is a group isomorphism, then we say that G is the internal direct product of these subgroups. Now we'll note that this map, which I've just defined here, may not even be a group homomorphism. Okay, so in fact, it's completely not it's not even guaranteed to be a homomorphism. Okay, we actually need that some commutativity of the, like, we want that the elements of these subgroups H sub I commute with each other to ensure that this mapping is even a group homomorphism, let alone an isomorphism. Okay, so now we state the direct product theorem. Okay, so we state the direct product theorem. So let G be a group and let H1 ... Hn be its subgroups. Okay, so given a set of subgroups H1 through Hn of G, we have that G is the internal product of these subgroups if and only if the following conditions hold. Firstly, each of the H sub i's is a normal subgroup of G. Okay, so all of these subgroups are normal in G. Secondly, we have that the product of these subgroups is equal to G. So H1 times H2 ... times Hn, where I say that the times as being a set product. So the product as sets, H1 times ... times Hn is equal to G. Okay, so the product of the subsets H1 through Hn is G. And then the third condition is that if let's suppose that A sub 1 belongs to H1, A sub 2 belongs to H2, etc., then if their product is equal to 1, so A1, A2, ... An is equal to 1 for some A sub I in the H sub i's, then A sub I is equal to 1 for all I. Okay? So this third condition is essentially the injectivity of this mapping from the direct product of the H sub i's into G, given by taking an element of the direct product, taking the product of all of its components. If that mapping is injective, that's our third condition, okay? So note this fact that the HIs being normal in G makes the set product of the H sub i's into a group, okay? And it actually ensures that this first condition, that all of these subgroups are normal in G, is essentially requiring that the mapping we defined from the direct product of the H sub i's into G, this mapping which sends A1 dot 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 AN into A1 A2 dot 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 AN, the mapping which sends A1 comma A2 comma dot 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 comma AN into A1 A2 dot 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 AN. Okay, so that mapping, this first condition that all of the subgroups are normal in G, ensures that that map is in fact a homomorphism. The second condition ensures that it's a surjective homomorphism. And the third condition ensures that it is an injective homomorphism. Okay. Now we also note the following results. So first of all, if G is a finite group, then we can replace condition 2 or condition 3, but not both. We can replace one of the conditions 2 or 3 by the condition that the cardinality of G is equal to the product of the cardinalities of the H sub i's. Okay? And then finally, we have the example, an important example of the Chinese remainder theorem. So from the direct product theorem, you can access the Chinese remainder theorem for relatively prime integers m and n, which are greater than or equal to 1. So if m and n are relatively prime integers greater than or equal to 1, we have that z modulo mnz is isomorphic to mz modulo mnz, direct product with nz modulo mnz. But these groups are in fact isomorphic to just z modulo nz, direct product with z modulo mz. So we have that z modulo mnz is isomorphic to mz modulo mnz, direct product with nz modulo, or not modulo, sorry, quotient. I'm saying modulo. Let me say quotient. I'll start over. So the Chinese remainder theorem, given relatively prime integers m and n greater than or equal to 1, we have that z quotiented by m and z is isomorphic to mz quotiented by m and z, direct product with nz quotiented by m and z, which is isomorphic to z quotiented by nz, direct product with z quotiented by mz. Okay? And so this Chinese remainder theorem actually follows as a result of the direct product theorem. And you need basically this trick that if the GCD of m and n is 1, you can find integers a and b such that am plus bn is equal to 1. Okay, so let's continue forward. We have another theorem now. Let G be a finite group. Write the cardinality of G in terms of its prime factorization. Cardinality of G is equal to p1 to the power n1 times dot 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 times p sub k to the power n sub k, where p1 through pk are distinct primes. Let H sub I be a pi Selov subgroup of G for all I. Okay, so for each of the prime factors of the cardinality of G, we take a p sub I Selov subgroup of G called H sub I. Then, if these H sub i's are normal in G for all I, if all of these p sub I Selov subgroups are normal in G, then G is the internal direct product of the H sub i's. So G is isomorphic to H1 cross H2 dot 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 cross H sub k. All right? So in other words, if H sub I is a unique pi Selov subgroup, because the uniqueness of the pi Selov subgroup is equivalent to the normality of the pi Selov subgroup in G, Then G is the internal direct product of its P-C-Love subgroups. Okay, so for each prime factor of the cardinality of G corresponds to a unique P-C-Love subgroup, then G is the direct internal product of its P-C-Love subgroups. Okay, and this proof is by the direct product theorem. We check all of the conditions, and the third condition, the injectivity, is the one that is less obvious, but I'm going to, it uses a second isomorphism theorem and some induction argument, but I'm actually going to skip this for now. Yeah, we're going to skip this for now. Okay, so I'm debating if I want to skip it or not. Okay, so let's just look at the injectivity real quick. So suppose that a sub 1 dot 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 a sub k is equal to 1 for some a sub i's within the h sub i's, which are the PIC-Love subgroups. We'll prove by induction that the cardinality of, well, wait a second, what? Okay, yeah, this proof is actually somewhat technical, so you can go back to the notes to review it, but yeah, it uses quite a technical argument, in fact. Okay, let's just quickly mention the argument. So we're trying to prove the injectivity of this map, which sends the direct product of the h sub i's into G via taking the product of all the components. Okay, we're trying to prove the injectivity of this map. So we suppose that we have an element in the kernel. We know it's a group homomorphism by checking condition 1, that the P-C-Love subgroups are normal. That was actually the assumption of the theorem, is that all of these P-C-Love subgroups are normal in G. So we know it's a group homomorphism. The surjectivity follows from, basically, we can replace the second condition with this cardinality of G is equal to the product of the cardinalities of the h sub i's, which is clear because these h sub i's are P-C-Love subgroups. So the product of their cardinalities is equal to the cardinality of G. Okay, so that's we'll replace the surjectivity condition with that, but then for the injectivity condition, we assume that take some element of the kernel of this map. So we have a sub 1 times dot 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 times a sub k is equal to 1 for some a sub i's within the h sub i's. And then we can use the second isomorphism theorem to show that the set product h1 set product dot 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 times h sub I is a divisor. The cardinality of that is a divisor of the product of the cardinalities of the h sub i's. Okay, this is by the second isomorphism theorem, since all of these h sub i's are normal in G. Okay. So then, using that, we can argue that the cardinality of h1 dot 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 hk minus 1 divides p1 to the k1, p1 to the n1 dot 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 p sub k minus 1 to the n sub k minus 1. So in particular, the cardinality of the set product h1 dot 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 h sub k minus 1, the cardinality is prime to p sub k. So the order of the element a1 dot 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 a sub k minus 1 has to divide the order of the group it lives inside h1 dot 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 hk minus 1. So the order of this element is prime to pk, but this element, since when you multiply this element by a sub k you get 1, we get that in fact this element is equal to a sub k inverse, so it has some order p sub k. It has an order which is a power of p sub k. So in particular its order must be 1. And so you get the injectivity of the math. So it's quite a technical proof and skimmed through the details there. But let's move on. Okay, so we have a nice application of this theorem to groups whose order is the product of two primes. So proposition. Assume that the cardinality of G is equal to P times Q, where P and Q are prime numbers, and P is strictly less than Q. Assume also that Q is not equal to 1 modulo P. Then G is cyclic. It's kind of a crazy proposition. So assume the cardinality of G is equal to P times Q, where P and Q are primes, and P is strictly less than Q. And assume also that Q is not equal to 1 modulo P. Then G is cyclic. Now I wanted to go through the proof of this because the proof uses a lot of technique, and so it's useful to go through. Okay, so we're going to go through it in the details. So let H sub P and H sub Q be some P C-love and Q C-love subgroups of G. Then the cardinality of H sub P is equal to P, and the cardinality of H sub Q is equal to Q, right? Because we have the prime factorization of the cardinality of G is just P times Q. So now we need to ask, are they normal, right? If we find out that they're normal, we're going to try and apply this theorem that we've just described, okay? So asking the question, are these P C-love subgroups normal, is equivalent to asking if they are unique, okay? So let's look at the third C-love theorem. We have that the number of P C-love subgroups of G is divisible or divides Q. Okay, so the number of P C-love subgroups of G divides Q. So it has to be either 1 or Q, right? Why is that the case? Because the number of P C-love subgroups of G, it's the case because Q is prime, right? If this number n sub P divides Q, since Q is prime, then n sub P is equal to 1 or Q. But we have that P is less than Q, and in particular, so P is less than Q, and we said that this number must divide, we said that this number is equivalent to, well, I'm not understanding this proof. So n sub P divides Q, so it's equal to 1 or Q, because Q is prime. Since P is less than Q, what was the second part of the third C-love theorem? We should have that n sub P is equivalent to 1 modulo P, right? N sub P is equivalent to 1 modulo P. That was the other third C-love theorem result. Yeah, so n sub P is equivalent to 1 modulo P. So since P is less than Q, we must have that Actually, yeah, I'm not understanding this proof. Q is less than Q. Oh, we assumed that Q is not equal to 1 modulo P. Okay, that's why. Okay, so we assumed that Q is not, I think the proof was not fully written correctly in the notes. So we assumed that Q is not equal to 1 modulo P. Since n sub P is equal to 1 or Q, if n sub P were equal to Q, we know by the second part of the third Sylow theorem that n sub P must be equivalent to 1 modulo P. But our assumption in this proposition makes that impossible. So we have that n sub P must be equal to 1. In particular, we have one P Sylow subgroup, so therefore it's normal. Okay, and so now we look at n sub Q. We have n sub Q, the number of Q Sylow subgroups. This number divides P. That's the third Sylow theorem. And it's equivalent to 1 modulo Q. But we assumed that P was less than Q. Okay, so since this number divides P, it's less than or equal to P. And so the fact that n sub Q is equivalent to 1 modulo Q implies that that it must be equal to 1. It cannot be equal to P. Right? N sub Q is either 1 or P. It can't be P because P is strictly less than Q. So the condition n sub Q is equivalent to 1 modulo Q forces us to have n sub Q is equal to 1, which means that H sub Q is normal in G. Okay? So therefore, we have that the condition of the direct product theorem that these subgroups are normal in G is satisfied, so we can apply the direct product theorem, okay, basically by this corollary that if we're looking at P Sylow subgroups over all the prime factors, then we just need to check their normality in G to show that G is an internal direct product of its P Sylow subgroups. So we get that G is isomorphic to H sub P direct product H sub Q. Okay, but H sub P is a group of order P. Okay, so it must be isomorphic to Z modulo PZ. And similarly for H sub Q, it's isomorphic to Z modulo QZ. So G is isomorphic to the direct product of Z modulo PZ with Z modulo QZ, which is isomorphic to Z modulo PQZ by the Chinese remainder theorem. So G is isomorphic to Z modulo PQZ, so it is cyclic. Okay, I apologize. I think there's a bit of an error in the proof. That's fine. Okay, so now let's move on to next section, nilpotent and solvable groups. Okay, so let's talk about nilpotent and solvable groups. First, we define the commutator. For two elements A, B, A and B of a group G, the commutator A bracket B, or A commutator B, is defined to be A, B, A inverse, B inverse. Okay, so the commutator of A with B, so bracket A comma B, is equal to AB, A inverse, B inverse. Given two subgroups, H and K, subgroups of G, the commutator subgroup, commutator H comma K, the commutator of H with K, is the subgroup of G generated by commutators of elements of H and K. Okay? So it is the subgroup of G generated by the set of commutators of elements of H and K and K. All right? So we have some properties of the commutator. So for the commutator of two elements, we have the property that the commutator of AB inverse is equal to the commutator of BA. Second property is conjugation. So if I take C commutator AB C inverse, so if I conjugate the commutator of A and B by an element C, then this is just the commutator of the conjugation of A by C and the conjugation of B by C. So namely, C commutator AB C inverse is equal to the commutator of CA C inverse with CB C inverse. The third property is that if the commutator of A and B is the identity element of the group, then A and B commute. In fact, this is if and only if. So A and B commute if and only if their commutator is the identity. As a corollary, a group G is abelian if and only if the commutator of G with itself is equal to the trivial group. So group G is abelian if and only if the commutator of G with itself is the trivial group. Okay? Now let's look at some properties of the commutator of subgroups, so the commutator subgroup. So first of all, if H and K are normal subgroups of G, so if H and K are normal subgroups of G, then their commutator subgroup, commutator of H with K, is normal in G. I'll remind you again that the commutator of H and K is the subgroup generated by commutators of elements in H with elements of K. All right, so it's commutators, the subgroup generated by the set of commutators A comma B, where A belongs to H and B belongs to K. This is the commutator subgroup H commutator K. And so we have this first property that if H and K are normal subgroups of G, then the commutator of H with K is a normal subgroup of G. The second property, if H is a subgroup of G, then the commutator of G with H is a normal subgroup of G. Okay, so if H is a subgroup of G, then the commutator of G with H is a normal subgroup of G. Third property, if H and K are subgroups of G, and the commutator of H and K sits inside of H, then K normalizes H. So K is a subgroup of the normalizer of H. All right? So again, let's state the third property. If H and K are subgroups of G, and the commutator of H and K is a subgroup of H, then K is a subgroup of the normalizer of H. In other words, K normalizes H. Okay? So if we look at the commutator H with K, if this is of course the subgroup generated by commutators A commutator B, where A belongs to H and B belongs to K. If this is a subgroup of H, then we're going to have that AB, A inverse, B inverse belongs to H whenever A belongs to H and B belongs to K. But that just implies that B, A inverse, B inverse belongs to H, right? So B, A inverse, B inverse belongs to H for all B within K, and for all A inverse within H, and so K normalizes H. So K sits inside the normalizer of H. So let's repeat this third property, that the commutator of H, if H and K are subgroups of G, and the commutator of H and K is a subgroup of H, then K normalizes H, or K sits inside the normalizer of H. Okay. So skip the proof of these. We now move to a crucial definition, the definition of a central series. Actually, before I move to this definition, let's state the second property one more time, or the first and second properties. So the first property, if H and K are normal subgroups of G, then the commutator of H and K is again a normal subgroup of G. The second property, if H is a subgroup of G, then the commutator of G with H is a normal subgroup of G. Okay? All right. So now let's look to this next definition, the definition of a central series. A central series for a group G is a chain of subgroups G0, G1, Gn, such that basically, okay, it's a descending chain of normal subgroups. Okay, so not normal subgroups, but let me just explain it this way. A central series is a chain of subgroups G, which contains G1 as a normal subgroup. G1 contains G2 as a normal subgroup. G2 contains G3 as a normal subgroup, which contains G sub n, which is the trivial group. Okay, so it's a chain of subgroups terminating a descending chain of subgroups, such that it's a descending chain of subgroups which begins with the group G and terminates with the trivial group. And this descending chain of subgroups is actually normal in G for all I. Okay, so actually I didn't even need to say normal subgroups. All of the elements of this descending chain of subgroups are normal in G. And then furthermore, the key property is that the commutator of G with G sub I is a subgroup of G sub I plus 1. Okay, so if you take, so this is a descending chain of subgroups, so G sub I plus 1 is sitting inside of G sub I. But if we take the commutator of G with G sub I, this is contained in G sub I plus 1. Okay? Alright, so let's just repeat this definition because I was pretty sloppy with it. Okay? So this is the definition of a central series. A central series for a group G is a chain of subgroups that is descending, beginning with the group G and terminating at the trivial group. It is a descending chain of subgroups which are all normal in G, such that the key condition holds that the commutator of G with G sub I is contained in G sub I plus 1. Okay? So commutator of G with G sub I is contained in G sub I plus 1. What does this condition tell us? This key condition tells us that G sub I quotiented by G sub I plus 1 is contained in the center of G quotiented by G sub I plus 1. Okay? Why is this the case? Well, okay, if we take, so G sub I quotiented by G sub I plus 1 is a subgroup of the center of G quotiented by Gi plus 1. Why is this the case? Well, if we take, is this correct? Let me think about this. Okay, so basically, consider the condition the commutator of G with G sub I is contained in G sub I plus 1, and quotient this condition by G sub I plus 1. Then we get that, okay, if we take the quotient map, it's a homomorphism. So the commutator of two elements, the image under pi of the commutator of two elements is just the commutator of their images. Okay, so the quotient homomorphism, do the homomorphism property, we're going to have that the pi of the commutator of A and B is equal to the commutator of pi of A with pi of B. Okay, so now look at the condition commutator of G with G sub I is contained in G sub I plus 1, and quotient this condition by G sub I plus 1. Okay, when we quotient this condition by G sub I plus 1, we're going to get that the commutator of G with G sub I, quotiented by G sub I plus 1, is just the commutator of G quotiented by G sub I plus 1 with G sub I quotiented by G sub I plus 1. And this is the trivial group, because it's contained in G sub I plus 1. The original commutator was contained in G sub I plus 1. So when we quotient everything by G sub I plus 1, we get that this commutator is trivial. So the commutator of G over G sub I plus 1 with G sub I over G sub I plus 1 is trivial. But that means that that this G sub I quotiented by G sub I plus 1 is contained in the center of G quotiented by G sub I plus 1, right? Because its commutator with G quotiented by G sub I plus 1 is trivial. So it must be contained in the center of that group, okay? So G sub I quotiented by G sub I plus 1 is contained in the center of G quotiented by G sub I plus 1. This is equivalent to this critical condition defining the central series that, again, it's a descending chain of normal subgroups beginning with G, ending at the trivial element, such that the commutator of G with G sub I is contained in G sub I plus 1 for all I. Okay, so we have a definition. A group G is nilpotent if it has a central series terminating in 1. Okay, so a group G is nilpotent if it has a central series which terminates in 1. We actually took the terminating at 1 to be part of the definition of the central series. Okay. Now, there's a special central series called the lower central series. Okay. So a group G is nilpotent if and only if the lower central series terminates in finite steps, or the lower central series is given as a descending chain of subgroups defined inductively by, it starts at G, and then G sub I plus 1 is equal to the commutator of G with G sub I. Okay? So you take the commutator of G with G sub I. This is going to be a subgroup of G sub I, so it's a descending chain. And furthermore, all of these subgroups are normal in G because they're commutators of something with G. So we have this descending chain of the form G, which is equal to G sub 0, contains G sub 1, which is equal to the commutator of G with itself, which contains G sub 2, which is the commutator of G with the commutator of G with G, so, and etc., where G sub I plus 1 is defined to be the commutator of G with G sub I. If this lower central series terminates in finitely many steps, okay, then the group G is called nilpotent. Okay? All right, so we'll return in a moment. Okay, so now we're going to do some examples of nilpotent groups. So first, any abelian group is nilpotent because the commutator of G with itself is trivial. Secondly, the direct product of finitely many nilpotent groups is nilpotent. Okay? And this follows from, if you look at two two central series, the central series for, let's say, G, and the central series for H, where G and H are nilpotent groups, then the direct product of G with H has the central series given by basically the direct product of the ith element of the ith subgroup of the central series for G and the ith subgroup of the central series for H. We take those direct products and we get a descending chain, a central series basically for the direct product of the two nilpotent groups. So basically you can form a central series for the direct product of finitely many nilpotent groups just by taking the term-wise direct product of their central series to form a central series for the direct product. Okay? So we have that the direct product of finitely many nilpotent groups is nilpotent. Okay. So we have an interesting exercise, which is that if G is a group and Z is the center of G, then if G quotiented by its center is nilpotent, then G is nilpotent. Okay? So, as a corollary, we have that every P group is nilpotent. Every P group is nilpotent. So the proof, this is an important proof, okay? We know that every P group has non-trivial center, all right? So, why does every P group have non-trivial center? Let's just review that. So, again, to prove that every P group has non-trivial center, we let G be a P group and let it act on itself by conjugation. Then the center of G is the set of fixed points with respect to this conjugation action. Fixed points like X superscript G, points that are fixed by the entire group G. And we have this crucial lemma. Since G is a P group, we have that the cardinality of the set of fixed points, X superscript G, is equivalent to X modulo P. It's equivalent to the cardinality of X modulo P. But the cardinality of X, since X equals G as a P group, the cardinality is divisible by P. So we get that the center is equal, the cardinality of the center of G is equivalent to 0 modulo P. But the center contains 1. So its cardinality has to be, since its cardinality is at least 1 and is equal to 0 mod P, its cardinality has to be greater than or equal to P, so it's non-trivial. It's a non-trivial center. Okay, so every P group has non-trivial center. So let G be a P group, then its center is non-trivial. So then G quotiented by its center is a P group of strictly less cardinality than the cardinality of G. Okay? So G quotiented by its center is a P group of order strictly less than the cardinality of G. And we can run induction on this and basically get a descending chain of subgroups by quotienting by their centers. Okay? And get a descending chain of subgroups which creates a central series. It has to terminate at 1. Okay. Now, why is G quotiented by its center normal? That's a good question. So, yeah, this was... Okay, so if we quotient G by its center, why is this normal? Yeah, so I'm going to have to come back to this, so I'm going to pause the recording. Alright, so for this corollary that every P group is nilpotent, we have the following proof. Since every P group has non-trivial center, okay, then we have that let G be a P group, its center is non-trivial, so G quotiented by its center is a P group of strictly less order. Now, by induction, you can descend down to 1 and get that, okay, you're going to end up with a trivial group. If you keep quotienting by the center, you're going to be reducing your cardinality strictly. So eventually you'll hit the trivial group. The trivial group is nilpotent. And then we use this exercise that if G quotiented by its center is nilpotent, then G is nilpotent, to basically go backwards through the induction and conclude that at every step we have a nilpotent group, because we're quotienting by the center at every step. So therefore, G must be nilpotent. So every P group is nilpotent. And as a corollary, we have that every finite direct product of P groups is nilpotent. Okay? So every finite direct product of P groups is nilpotent. Now we have a theorem, which is the classification of finite nilpotent groups. Basically, this theorem, classification of finite nilpotent groups, states that there are no other finite nilpotent groups. So every finite nilpotent group is a direct product of P groups. Every finite nilpotent group is a direct product of P groups. This is the classification of finite nilpotent groups. Okay, so now we are going to go through some lemmas which are used to prove this classification theorem. The first lemma is consider a nilpotent group G and let H be a proper non-trivial subgroup of G. Then H is not equal to its normalizer. So, in particular, H is strictly contained in its normalizer. Okay? So the proof of this is instructive. We take a central series for G. If we have a descending chain of normal subgroups which satisfy the condition that the commutator of G with G sub I is contained in G sub I plus 1. We look at this central series and we find an index I such that G sub I does not contain H. G sub I is not contained in H. So G sub I is not contained in H, and G sub I plus 1 is contained in H. Okay, we can do this because the central series terminates at 1. So we find an I such that G sub I is not contained in H, and G sub I plus 1 is contained in H. Then, the commutator of H with G sub I is a subgroup of the commutator of G with G sub I, which is by the central series, is a subgroup of G sub I plus 1, which is a subgroup of H. So H, the commutator of H with G sub I, is a subgroup of H. Okay? Now, we have that, so since the commutator of H with G sub I is contained in H, we have that G sub I is contained in the normalizer of H. G sub I is contained in the normalizer of H, because the commutator of H with G sub I is contained in H, so G sub I is contained in the normalizer of H, but G sub I is not contained in H. So, the normalizer of H is strictly larger than H. Okay, the second lemma, let G be a group, and let K be a PC-love subgroup of G for some prime P. And let's define H to be the normalizer of K. Then the normalizer of H is itself. In other words, we have for G a group and K a PC-Love subgroup of G, we have that the normalizer of the normalizer of K is equal to the normalizer of K. Okay? And the proof is if we take an element of the normalizer of K, then we have that K is a PC-Love subgroup in the normalizer of K, but also some element, let's call it A, some element AK A inverse is also a PC-Love subgroup in the normalizer of K. Right? So let's think about this. Okay, so we have an element A in the normalizer of K. So then, if this element is in the normalizer, that means that it normalizes the normalizer of K. So okay, so what does that mean? That means that if we conjugate now I'm getting stuck here. Okay, so we look at the normalizer of K. K sits inside the normalizer of K. Let A be an element of the normalizer of the normalizer. Then AK A inverse is a subgroup of the normalizer of K, because AK A inverse is contained in A normalizer of K A inverse, which is equal to normalizer of K, because A is an element of the normalizer of the normalizer. So K and AK A inverse are both PC-Love subgroups in the normalizer of K. But K is normal in its normalizer. K is a normal subgroup of its normalizer. So K is unique by the C-Love theorem. Okay? I believe it was second C-Love. Second C-Love theorem. Yes. So we have that we must have that K is equal to AK A inverse. In particular, A belongs to the normalizer of K. So we started with A belonging to the normalizer of K, and showed that K is equal to AK A inverse, so A belongs to the normalizer of K. So in particular, the double normalizer of K is equal to the normalizer of K. Then we can prove this classification of finite nilpotent groups theorem. So let G be a finite nilpotent group. To show that G is isomorphic to a direct product of P groups, we just need to check that G has a unique PC-Love subgroup for every P prime. Okay? In other words, we need to check that any PC-Love subgroup is normal. So let K be a PC-Love subgroup of G. Then the normalizer of K is equal to the normalizer of K by our lemma. So, furthermore, the normalizer of K is strictly larger than K by our first lemma. So the normalizer of K is strictly larger than K by our first lemma. Again, since G was nilpotent, if G is nilpotent, then for any proper non-trivial subgroup is strictly contained in its normalizer. Okay. So we have that any P-C-Love subgroup is normal, and furthermore, the normalizer of K strictly contains K. So we have the normalizer of K is equal to the normalizer of K. And since these normalizers just keep getting bigger and bigger, okay, so these normalizers are subgroups of G. These normalizers are going to keep getting bigger and bigger for any proper non-trivial subgroup because G is nilpotent. The normalizers keep getting bigger, so we must have that since the normalizers keep getting bigger, but also we have this property that the normalizer of K is equal to the normalizer of K, we must have that the normalizer of K is equal to the entire group G. So in particular, K is normal in G. So all P-Love subgroups of G are normal, and therefore G is isomorphic to a direct product of P groups, namely the P-C-Love groups of G. If G is a finite nilpotent group, this has been the classification of finite nilpotent groups. Okay, so now we have the derived subgroup, another crucial definition. Okay, so this is definition of the derived subgroup. So let G be a group. The subgroup commutator of G with itself, commutator of G with G, is called the derived subgroup of G. Note that the commutator of G with itself is always a normal subgroup of G, since if you conjugate an element commutator of AB, so let's conjugate by an element C, so we take C commutator of AB C inverse, we get the commutator of CA C inverse with CB C inverse. So we have that the commutator subgroup, the derived subgroup, I should say, the derived subgroup commutator of G with itself is a normal subgroup of G. Okay, and it's called the derived subgroup of G. The quotient group, G quotiented by the commutator of G with itself, is an abelian group, and it is called the abelianization of G. So the abelianization of G is G quotiented by its derived subgroup, G quotiented by commutator of G with itself. Okay, so we have an exercise, namely, given any normal subgroup of G such that G quotiented by this normal subgroup is abelian, we must have that this normal subgroup contains the derived subgroup. Okay? So if N is any normal subgroup of G such that G quotiented by N is abelian, then N must contain the derived subgroup commutator of G with itself. Note that the derived subgroup is sometimes denoted G prime, like a derivative symbol. G prime is commutator of G with itself. Okay? All right. That's kind of an interesting notation because if you think in quantum mechanics, recall that the commutator of the position and momentum operators is like a derivative operator. So something, probably maybe the name stems from that. Who knows? Maybe not. Okay, anyways, that was a random tangent. Okay, we have a definition. The derived series of G is the following descending series. It is the series starting at G and then descending G superscript 1, G superscript 2, etc., where the superscripts are in parentheses, like the derivative, defined inductively via G superscript I plus 1 is equal to the commutator of G sub I with itself. Okay, so the derived series we take inductively to get, it's a descending chain of subgroups where the next element is formed by the commutator of the previous element with itself. This is in contrast to the central series, or the lower central series, you could say. The lower central series where the next element is formed by the commutator of the previous subgroup with G. We have that the derived series is the series defined inductively as a descending chain of subgroups where the next element is given by the commutator of the previous element with itself. Okay, so we say G superscript I plus 1 is equal to G superscript I prime, kind of mimicking the derivative notation, which is the commutator of G superscript I with G superscript I. Okay, so we have a definition. Solvable groups. A group G is said to be solvable if its derived series terminates in the trivial group after finitely many steps. So if the derived series terminates in the trivial group after finitely many steps, the group G is said to be solvable. We have an exercise that there's an equivalent definition of solvability, namely, a group G is solvable if and only if there is a series, a descending series of subgroups beginning at G and ending at the trivial group, such that the elements of this descending chain of subgroups, so if you look at the ith element and the I plus 1th element, then we have that the I plus 1th element is normal in the ith element, not necessarily in G, just normal in, so the next element of the sequence is a normal subgroup of the previous element of the sequence, but not necessarily normal in the full group G. So you have a descending chain of subgroups, a descending chain of subgroups starting at G, terminating at the identity, terminating in the trivial group, which are normally, or which contain, so it's a descending series, which basically each element of the series is normally contained in the previous element of the series, not necessarily in the full group G. With the following property, with the property that G sub I quotiented by G sub I plus 1 is abelian. Okay, so G sub I quotiented by G sub I plus 1 is abelian. Okay. Note that if you take a group and quotient by its derived subgroup, so you take a group G and quotient by commutator of G with itself, this is an abelian group called the abelianization of G. Okay, so we have this exercise that a group G is solvable, i.e. its derived series terminates in finitely many steps, if and only if there is a series starting at G and terminating at 1, such that each element of the series is a subgroup which is normal in the previous element of the series, not necessarily normal in the full group G, just normal in the previous element of the series. And this descending chain of subgroups satisfies that G sub I quotiented by G sub I plus 1 is abelian for all I. Okay? And the reason why this exercise is true is because if you take, it's a direct result of the previous exercise, which is that if N is a normal subgroup of G, and G quotiented by N is abelian, then N contains the derived subgroup. Okay? So we have this informal note, which is that a solvable group can be built out of abelian groups. Okay, so it is the natural way to generalize the notion of abelian. Informally, a solvable group can be built out of abelian groups. So it is the natural way to generalize the notion of abelian. Now our first example is that every nilpotent group is solvable. Okay, so being nilpotent is stronger than being solvable. Okay, why is this the case? Well, if you look at the commutator of G sub I with G sub I, or G superscript I with G superscript I in this derived series, this has to be contained in the commutator of G superscript I with G. Okay? So we see that the central series is descending slower than the derived series. So if the central series terminates, then the derived series certainly must terminate. So every nilpotent group is solvable. Secondarily, we have the second example. Any subgroup of a solvable group is also solvable. Okay? Any subgroup of a solvable group is also solvable. Okay? To prove this, you take the derived series, take the derived series for G, look at the subgroup H, and set basically the chain, set a not the derived series, but this series just equal to G superscript I intersect H. Okay, so G superscript I intersect H. So you just intersect this descending series for G, which satisfies the condition that, okay, it's a descending series such that each element of the series is normal in the previous element, and the quotient of G sub I with G sub I plus 1 is abelian. You take that series for G and intersect every element of that series with H, right? Intersection of two subgroups is a subgroup. You intersect that series with H and you get a series for H that terminates in 1. Okay? And it still satisfies the condition that HI quotiented by HI plus 1 is still abelian. Okay? So now we have to prove that. So, moving on. The quotient of a solvable group is solvable. Okay? So any quotient of a solvable group is solvable. If n is a normal subgroup of a group G, and G is solvable, then the quotient G over n is solvable. Why? You look at the quotient homomorphism from G to G quotient n, and you take the image of the derived series under the quotient homomorphism. Okay, so you take the image of this series for G under this quotient homomorphism, gives you a series for G quotiented by n. So the quotient of a solvable group is solvable. Now we have an important lemma. Namely, if n is a normal subgroup of G, such that n and G quotiented by n are solvable, then G is solvable. Okay, so if n is a normal subgroup of G, such that n and G quotiented by n are solvable, then G is solvable. Okay, so the proof is instructive. We take the series for G quotiented by n and pull it back to G via the quotient homomorphism. To take the inverse of the quotient homomorphism, we get a series starting in G and terminating in n. Then we use the solvability of n to extend this series to the identity. Okay? So we have an interesting example Assume G is a finite group whose cardinality is of the form PQ, where P and Q are primes, and P is less than Q. Then we have that any Q C-love subgroup is normal in G, as we discussed in the previous case. And so the cardinality of G quotiented by this Q C-love subgroup, let's call it H sub Q, the cardinality of G quotiented by H sub Q is equal to the prime P. We can quotient because this H sub Q is normal. So both H sub Q, which is a cyclic group, so order Q, which is Q is prime, and G quotient Q, or G quotient H sub Q, G quotient H sub Q is of order P, which is prime, so both of these are cyclic, therefore they are both abelian, therefore they are both solvable. So by the lemma, recall the lemma is if n is normal in G, such that n and G quotiented by n are solvable, then G is solvable. We have that, G is solvable. G is solvable if G is the product, if the cardinality of G is the product PQ, where P and Q are primes. Now note, such G is nilpotent, by the classification of nilpotent groups, such G is nilpotent if and only if G is isomorphic to the direct product of Z modulo PZ with Z modulo QZ. So in particular, G has to be abelian if it's nilpotent. So that's much more restrictive, but in the case that G is always solvable if its cardinality is the product of two distinct primes. Okay, but if G is nilpotent in this same scenario, it has to be isomorphic to direct product of Z modulo PZ with Z modulo QZ. In particular, it has to be abelian. Okay, so that covers the section on derived subgroups and solvable, so nilpotent groups and solvable groups. Now we're going to move to the symmetric and alternating groups. So let's do that in the next recording. Okay, so I'm going to cover this somewhat quickly. This next section is on the symmetric and alternating groups. So we first have the definition of a K-cycle, a permutation sigma within S sub n. S sub n is the set of permutations of the set 1 through n. So a permutation sigma within S sub n is called a K-cycle if there are some k distinct numbers in the set 1, n, which are cyclically permuted by sigma. So namely, sigma sends a1 to a2, sends a2 to a3, sends ak minus 1 to ak, and then sends ak to a1. And the other elements, so the elements of the complement of these a sub i's in the set 1 through n, are fixed under sigma. Okay, so that's called a K-cycle. And we write sigma is equal to parentheses a1, a2, ak for a K-cycle. Okay. So now continuing forward. We have an equivalent notion of a two-cycle. So a two-cycle is also called a transposition. We have the following proposition: every element of S sub n is a product of disjoint cycles. Every element of the symmetric group is a product of disjoint cycles. Okay? So the proof of this, we're going to consider an arbitrary element sigma of the symmetric group, and let H be the cyclic group generated by sigma. Then H acts on the set 1 through n by the restriction of the canonical action of the symmetric group on the set 1 through n, which we're going to call X. X is going to be the set of 1 through n. So consider the orbits of this group action of the cyclic group generated by sigma. These orbits, consider all the orbits which are different from singletons. If these orbits are singletons, then sigma simply fixes these elements. So consider all the orbits which are different from singletons. Then sigma must permute cyclically the elements of each of these orbits. Okay, so if you look at an individual orbit, okay, and look at how sigma works on this orbit, right? We have that the elements of this orbit are of the form sigma to the power n a, where a is an element. So let a be an element of some orbit which is not fixed. Then the elements of this orbit are sigma to the power n times a, okay? And in particular, applying sigma to such a set will cyclically permute the set. Okay, so applying sigma to the set of an orbit of one element will cyclically permute that set. And since the set X is partitioned, is a disjoint basically is a disjoint union of the orbits, we have that sigma is the product of all of these cyclic permutations of each of these different orbits. And note that disjoint cycles commute. So this proof makes sense. Sigma is the product of each of these cyclic permutations. The product of disjoint cycles commutes. Okay. Now we have the definition, which is the cycle type of a permutation. If sigma belongs to the symmetric group, so sigma in Sn is the product of disjoint cycles of lengths k1, which is greater than or equal to k2, greater than greater than or equal to k sub r, which is greater than or equal to 2, we call these sequences, this non-strictly descending sequence, k1 through kr, this non-strictly descending sequence, k1 through kr, which represents the lengths of the disjoint cycles whose product is sigma, then this strictly or non-strictly descending sequence k1 through kr is called the cycle type of sigma. It's called the cycle type of sigma. Okay? Now, given any k cycle, okay, so now we're going to move on to another key note, which is that take a k cycle, sigma. So sigma is equal to a1 through an. So a1 dot 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 an. This is a k cycle. Then, or I should put sigma is equal to parentheses a1 through an. And then let tau be an arbitrary element of the symmetric group. Then if we conjugate by sigma by tau, so tau sigma tau inverse, this is still a k cycle, and it's given by, in parentheses, tau of a1, tau of a2, dot dot dot, tau of ak. All right? So conjugating by tau is basically the cyclic permutation of the images of the a sub i's under tau. All right? So we have as a proposition, two permutations, sigma and tau in S sub n, are conjugate if and only if they have the same cycle type. Okay? So how do we do this? Well, we break down, first of all, we just note, the proof boils down to one key fact, which is that if you conjugate sigma, let's say sigma is the product of n elements, sigma 1 dot 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 sigma n. The conjugation of sigma by some element tau in the symmetric group, tau sigma tau inverse, is equal to tau sigma 1 tau inverse, tau sigma 2 tau inverse, dot dot dot, tau sigma n tau inverse. So in particular, this recall that if we look at the group action of conjugation of G on itself, where in this case G is the symmetric group, then every by the homomorphism, the corresponding homomorphism of this group action is actually, its image is contained in the automorphism group of G. So conjugation by a group element is in fact a group automorphism. Okay, so theta sub, with respect to this group action, theta sub A, which sends sigma to A sigma A inverse, this map theta sub A is a group automorphism. Okay, so we use that fact to basically prove that two permutations, sigma and tau in Sn, are conjugate if and only if they have the same cycle type. Okay, the way this is done is by constructing tau and using this property that tau sigma tau inverse is equal to the permutation tau of A1 ... tau of AK in parentheses. Okay, so basically if sigma is parentheses A1 through AK, then tau sigma tau inverse is parentheses tau of A1 ... tau of AK. All right? So using that formula and the fact that the conjugation is a conjugation by a fixed element is a group automorphism, we can basically construct element to conjugate two permutations if and only if they have the same cycle type. So we can use that to prove the proposition that two permutations, sigma and tau in Sn, are conjugate if and only if they have the same cycle type. Now we have an exercise that any k cycle is a product of k minus 1 transpositions. Okay, so this is an exercise. Any k cycle is a product of k minus 1 transpositions. We have that the parentheses A1 through AK is equal to the transposition A1 AK times the transposition A1 AK minus 1 ... times the transposition A1 A2. Okay, so any k cycle is a product of k minus 1 transpositions. Parentheses A1 through AK is equal to parentheses A1 AK times parentheses A1 AK minus 1 ... times parentheses A1 A2. Okay, note that these transpositions are not disjoint. So as a corollary, every element of the symmetric group sigma within Sn is a product of transpositions. Okay, so now let's define the permutation representation. For every element of the symmetric group, we may associate the linear automorphism from Rn to itself, which permutes the standard basis of Rn. Okay, so we have a permutation matrix. With every permutation, sigma in Sn, we can associate the corresponding permutation matrix, which permutes the standard basis of Rn. I guess we're associating the linear automorphism represented by this matrix. Okay, this gives us a group homomorphism from Sn into GLNR, which sends sigma to its associated permutation matrix, which again permutes the standard basis of Rn via sigma. So this group homomorphism is called the group homomorphism from Sn into GLNR is called the permutation representation of Sn. Okay, so now let us look at a composition of homomorphisms. We look at the permutation representation of Sn and then compose with the determinant map. Okay, now note that the determinant of a permutation matrix is plus or minus 1. So by composing with the determinant map, we get a homomorphism from Sn into z modulo 2z, namely plus or minus 1 in this case, which is isomorphic to z modulo 2z. So we have Sn maps into GLNR, which maps into plus or minus 1 by sending an element sigma of the permutation group to its associated permutation matrix, and then taking the determinant of this matrix. It will give us plus or minus 1. This is a group homomorphism, and it's called the sign homomorphism of Sn. Okay? We have the definition that sigma, an element of this symmetric group, is even if its sign is +1, and sigma with an Sn is odd if its sign is -1. We then define the alternating group A sub n as the kernel of the sign homomorphism. This is the set of even permutations. Note that because it's the kernel of a homomorphism, the alternating group is a normal subgroup of S sub n. Okay? So, right, so we've defined the alternating group as the kernel of the sign homomorphism, which is the set of even permutations. It's A sub n, it is a normal subgroup of S sub n. Okay, and by Lagrange's theorem, we can show that the cardinality of A sub n is just the cardinality of S sub n over the index of A sub n and S sub n. The index of A sub n and S sub n is just the cardinality of z modulo 2z, so it's just 2. Meaning that the cardinality of the alternating group is just n factorial over 2. Okay? Now, we introduce a lemma. Lemma is that A sub n is generated by 3 cycles. Note that a 3 cycle is an even permutation. Okay? So, this lemma, the alternating group, is generated by 3 cycles. I'm going to skip the proof for now because I'm running out of time. It's getting late. We have another lemma that every 2 3 cycles are conjugate in A sub n when n is greater than or equal to 5. Okay, so any 2 3 cycles are conjugate in A sub n when n is greater than or equal to 5. So with these two lemmas, first, A sub n is generated by 3 cycles. Second, every 2 3 cycles are conjugate in A sub n for n greater than or equal to 5. We have that the alternating group for n greater than or equal to 5 is simple. What is a simple group? Let me define it. Okay, so a group G is called simple if the trivial group and G are the only normal subgroups of G. So basically, G has no non-trivial normal subgroups. Then G is called simple. Okay? Now, so we repeat this theorem. For n greater than or equal to 5, the alternating group is simple. The proof uses these two lemmas. First, that the alternating group is generated by 3 cycles. And second, that every 2 3 cycles are conjugate in A sub n for n greater than or equal to 5. The proof is kind of a technical computation, which I'm not going to go over. But the point is that we have a first non-trivial example of a simple group. And I'll restate the definition of a simple group. A group G is called simple if it contains no non-trivial normal subgroups. Okay? Like, besides one in itself. Okay? Now, there's this interesting exercise, which I'll mention, which is that if G is an abelian or solvable group, if G is abelian or solvable, then G is simple if and only if G is isomorphic to Z mod PZ for a prime P. So I think this exercise is obvious if G is abelian, but in the case that G is solvable, it's kind of interesting. So it says that G is simple if and only if G is isomorphic to Z mod PZ for a prime P. Okay, and I think that will be everything. Okay, actually, as a corollary of as a corollary of A sub n being simple, we have that A sub n is not solvable for n greater than or equal to 5. A sub n is not solvable. Why? Because if you take the commutator of A sub n with itself, the commutator of A sub n with itself is not trivial, because A sub n is not is not abelian when n is greater than or equal to 5. But the commutator of a sub n with itself is a normal subgroup of a sub n. So, if we try to take the derived series, then it will not terminate, basically. Because since a sub n is simple, the commutator of a sub n with itself must be equal to a sub n, since it's a normal subgroup of a sub n, and a sub n is simple, so it has no non-trivial normal subgroups. So therefore, the derived series will not terminate, and so this alternating group is not solvable for n greater than or equal to 5. And in particular, that implies that S sub n is not solvable. So the symmetric group is not solvable for n greater than or equal to 5. It turns out that the symmetric group is solvable for n less than or equal to 4. Okay? Symmetric group is solvable for n less than or equal to 4, but it is not solvable for n greater than or equal to 5. And the reason for this is we know that the alternating group is not solvable for n greater than or equal to 5, and the quotient of the symmetric group by the alternating group is just isomorphic to z modulo 2z, and this is solvable. So if S sub n were solvable, since the quotient of S sub n by A sub n is solvable, it's just isomorphic to z modulo 2z, then if the symmetric group were solvable, then the alternating group would be solvable. Okay? So we have that the alternating group is not solvable. Okay. Yeah, that's all that I need to cover for now. Okay. Have a nice day.